Mute. You're on mute. Yeah, please. Oh, is back on mute. Yeah, please tell me. Nice.
Oh, very good, very good. So you're teaching computer networks, you're teaching TCP/IP. Undergrad, TCP/IP you'll be covering?
Yeah, TCP/IP, all the layers, like network layer, transport layer, and data link layer.
Okay, perfect. Very good, very good. So do they do any programming assignments?
Yeah, they do,
sure.
sir.
No?
Actually, I am not asking them to do it in C language, but we use a network simulator for simulating some of these. And also some C codes for stop and wait and go back and select to repeat.
Oh, very good.
And some quick stuffing, framing.
Nice.
These stuff I am just trying to do.
Yeah, these are all very classic things. Which textbook are you following? Already? Yeah.
So I think we'll.
Yes, please.
Yeah. Start, sir. I think the
please. Yeah.
also ready. I think we can.
Yes. So everyone has access to the slides now, so that you know.
Yeah. I think because all are here only in the hall only.
Okay. Very good. Okay. So shall I start?
Ready? Okay.
Yes.
Good afternoon, all of you. And we have with us Professor Sundar Varunka from IIT Hyderabad. He is Associate Professor, Department of Electrical Engineering, IIT Hyderabad, and he is working from 21 to 8. And he is a communication engineer with a proven track. We have with us Professor Sundar Vanka from IIT Hyderabad. He is Associate Professor in the Department of Electrical Engineering. And he is a communication engineer with proven track record in wireless system design and implementation, and a strong academic research background in the mathematical modeling, design, simulation, and performance evaluation of wireless systems and networks. Inventor and co-inventor of 5 US patents, and his doctoral work has resulted in 1 book chapter, 1 patent application, 3 journal papers, and 8 conference papers. His Google scholar citations will be around 500, 499 or 500, and his H index is 9 and I-10 index is 7. He has done his PhD from University of Notre Dame in 2000, from 2007 to 12, and BTech and MTech from Electrical Engineering IIT Madras, and I think it is a dual degree program from 98 to 2003. Sir, please correct me if I am wrong.
No, you're correct.
So yes. After his BTech, he has joined as a design engineer in Red Pine Signals, Hyderabad, and he is main architect in developing physical layer algorithms, VLSI architectures for IEEE 802.11, which is Wi-Fi standard, and also WiMAX standard 802.16, and UWB 802.15 3A. Chipsets, and he also developed some techniques for noise adaptive channel decoding in MIMOs and OFDM system. He is also designed some algorithms and VLSI architectures for high throughput Reed-Solomon decoders, low complexity stream weighing techniques for soft output MIMO detections, near optimal algorithms for soft output MIMO detection, and design is low complexity VLSI architecture, and low complexity channel estimation algorithms for MIMO and OFDM. And after his PhD, I think he has joined as a principal scientist and in Broadcom actually in Sunnyvale, California, I think, United States. And he's the main architect in design, implementation, and productization in physical layer signal processing algorithms in hardware and software. Developed and owned a high impact features such as hardware software based interference mitigation, high performance wireless LANs, Bluetooth, coexistence algorithms on flagship VLAN, Bluetooth combo SoCs, and extensive experience in design of laboratory tests to evaluate RF systems, and so on. If I start reading, it takes some more time. But with this small introduction, I invite Professor Sundarvanka to present a mathematical model on point process. Thank you, sir. Please.
Yeah. Thank you very much, Sai Prakash Garu, for the very long, very nice introduction. It's really nice to have an opportunity to talk about this topic. This topic is one of my topics that I'm currently interested in. So what I will talk today is kind of a mathematical perspective on how to model wireless networks in particular, correct? And in this particular course, we are interested in aerial communication networks. So we will also look at how we will consider aerial communication networks, particularly in the later half of this session, okay? So given that this is a slightly mathematical course, I really thank Professor Sai Prakash Garu for giving us a chance to kind of gain this platform to kind of gain a little bit of exposure as to how people receive it, because some of these things we believe are a very interesting tool, and particularly like I was telling Professor Garu before the talk, that when combined with machine learning, you can actually do a lot with these kinds of mathematical tools. Okay, so what I will talk about now will be I've titled my talk as a gentle introduction to point processes, and you'll see why I'm calling it gentle, as we go by. What I will touch upon are some of the very, very basics of point processes and motivate why you need point processes and what properties of these point processes are relevant to an engineer, okay, for a communication engineer. And after that, my PhD student, Taiba, who's also on this call, has prepared an extensive list of demos, and simulations and so on. And she'll also present some of our work in this context to kind of give you a flavor for how you might apply some of these techniques in for a real UAV related problem. Okay. So with that in mind, let's start out. So this talk will basically be like a 3-part talk. So feel free to interrupt me because I like to see audience participation just to make sure that, I'm not going too fast or I'm not explaining certain things as clearly as they would want. Okay. So what we'll do is we'll start out with why you need these point processes at all. And then we will look at some of probably the most basic family of point processes called the binomial and the Poisson point process. And then I'd like to dwell a little bit on the value of what is called ergodicity. Okay. So I'm told that many of you have a background in basic probability theory, and that is all I will assume. In fact, I think there is maybe one equation which contains the binomial distribution in this entire talk. So, and maybe one equation containing the Poisson distribution. Okay, I couldn't avoid it, but it's good to kind of have something which is very, very relatable to, especially to undergrad audiences, right? So with that, I will start out. So let's start out with from basics, right? So if I have a wireless network, okay, and you look at it from a physical layer perspective, right? Let's say there are 2 nodes, A and B, which are separated by some distance D. Okay, so I'm moving my pointer. So there's a distance D, okay? And what you would expect is the signal that is leaving the antenna at A will not have the same strength as the signal reaching the antenna at B, correct? And the difference between these 2 signal strengths is what we call the path loss, because the signal had to travel some distance from A to B. Okay. Now, if you talk to a physics person or if you talk to electromagnetics person, they will say, no problem, you write the Maxwell's equations, you write the boundary conditions and you solve it, or you do it numerically and you find out, depending on the particular environment, how exactly does the signal attenuate, and what kind of scattering happens and so on, right? But we are interested in a slightly more empirical / more engineering approach, where without doing all of that, right, we want to be able to say something about how do I design a link which is going to operate with a distance of 1 kilometer with a input power of 10 watts, maybe with a link margin of 10 dB. I'm sure many of you have done those calculations, and those calculations depend on models, correct? So we have models for the path loss, and we model various effects included in that path loss, right? So this picture that you see here contains those effects. So what it has is, so the y-axis says channel gain, but actually it is the loss if you think about it. The negative of the gain is loss, right? And it is plotted in a log scale. I'll come to log scale in a minute why it is, but basically there's a log scale on the y-axis. And on the x-axis, there is distance that's also plotted in the log scale. Okay, so the way we model this is, if you think of this overall channel gain or the overall path loss as a distance-dependent path loss, which is coming purely because you're moving away from the transmitter, then there is some amount of loss because there are buildings or obstructions in the middle, the shadowing loss. And then there is the scattering loss that is coming because of multipath propagation. Okay, so we are not going to go deep into what exactly those are, but we all know that it is a product of these three, and it makes sense to understand where these three things are actually falling in such a plot. Okay, so if you take a logarithm, you can see that anything that is a product will become a summation when you add a logarithm. When you take a logarithm on both sides, right? So this becomes log of PL plus log of PLW shadow and log of G. Correct? That's the overall thing. So if you just consider the first term, PL of D, that is essentially just the attenuation with the distance. Okay, so we model that with distance to the power minus alpha, where alpha captures the environment and alpha is called the path loss exponent. Typically alpha is 2, 2.5, 3, 3.5, and so on. Okay, depending on the amount of obstacles and reflections. Okay, so if I just look at that, just this one, okay, the one that I'm highlighting. Are you able to see my highlighting? Yeah, great, great. So if you just look at this one that I've highlighted, okay, that line, if I take the log of that, this will become minus alpha log D. So log of this path loss is proportional to minus alpha log D, correct? So that is basically a straight line, this dashed line, correct? Because that's why we can take, if you take log D on the x-axis and you take a log of the channel, this gain on the y-axis, this will be a straight line. This dashed line will be a straight line. Okay. Now, what happens is that effect is completely different from the effect which is coming because of obstacles, which is a shadowing loss. And typically the log of the shadowing loss is considered to be a Gaussian random variable, something called log normal shadowing. Again, we will not get into too much of that, but basically we need to understand that this term, because I've taken logarithm here, it will add to the path loss here, correct? Because I've taken log of this, the total loss will be the log of this plus the log of this term. The log of that term will be some random variable. So it will keep on adding some randomness to it. But the important thing to understand there is the shadowing is a little more sticky, correct? Which means if you are behind a building for a while, you will be behind the building for some time. So that effect is more correlated, right? Okay. And the last effect is the scattering effect, which is coming because of multipath propagation. Okay. So that again, we have all these random variables called, in this case, we have taken a gamma distributed random variable. It doesn't matter what exactly it is, but basically it is some random variable that models the fact that the antenna hitting a particular signal hitting a particular antenna comes because of several reflections from the neighboring environments. Okay. So this dashed line is purely the distance part because you're moving away from the transmitter. This sort of wavy line is because it is coming because of different obstacles. This jiggly line, which is moving, which is changing very fast, is because of multipath fading, which is basically scattering effects. Okay. So the question here is, of all these three effects, you can see that in themselves, they cannot alter the fact that when I increase the distance, the signal is falling, correct? The amount of energy received is falling, correct? So what happens is, you can think of these two terms as some kind of a correction term to this underlying dominant term, which is the path loss term. Okay. So if you have a path loss, which is coming d to the minus alpha, I will add some margin on top. I'll add some extra variable on top. That is my extra gain. Okay. Right. And that is typically random. Okay. We can model that. But remember that these two things don't depend on the distance, but this thing does depend on distance. Then the question that arises is, can this distance be random? Right? So if you think of a tower, like people, all of us are sitting in our rooms now and attending this call. Imagine the different people having their phones, and each of the phones is probably connected to a different tower because you may have a different carrier. Like one person may be connected to a Geo network, one person may be connected to an Airtel network, another person may be connected to a BSNL network. So if I think of all of you people and as individuals having phones, and I look at the link distance from each phone to its tower, it is random because it depends on the person that I choose. Correct? So technically, you will see that this distance of the distance between two objects in a wireless network, like A and B, transmitter and receiver, can be random. Okay. So let's see what it means in a UAV context. Okay. So whether you deploy the UAV in an urban environment or you have different remote controls that you can possibly use, right? You will have a situation where you take a UAV, and if I want to ask the question, what are the distances of this UAV from different base stations? Okay, so these are depending on the locations of these base stations in a given neighborhood. Okay, this UAV will have a certain set of distances. Correct. So if I gave you the distance, the location of BS1, the latitude, longitude of BS1, BS2, BS3, and I also gave you the latitude, longitude, and maybe the height of UAV, which is available, by the way. All these UAVs have a GPS module, right? You can actually compute where exactly this GPS is located with respect to all of these objects, right? But then what happens is, if I, let's say, hover around in a flight path here, okay? If I come here, then these distances will become different, correct? So these distances are time varying. So if I move to a different neighborhood, I will see a different collection of base stations in that neighborhood. So depending on the neighborhood, these collections of distances will look random to me, correct? So if I'm in one area, I'll have these, one location, I'll have these distances. If I'm in another location, I'll have some other distances to the base station, correct? So fundamentally, in a network, the distances, as we saw just now, play an important role in the propagation and the amount of signal energy reaching the receiver. And the distances in a network can be random because they're determined by many things, including obstacles, including the fact that you have infrastructure that's deployed, in fact, mobility of the client and so on, right? So this leads us to asking an even bigger question, right? What happens if you have a much bigger set of UAVs that want to connect to different base stations? So I've taken 3 examples. So this particular example that you see here is one of those drone displays, correct? So if you have seen how drone displays work, they are essentially pre-programmed to display a certain light at a certain time, okay, and be in a certain position at a certain time. Now to do that, you need to make sure that all these drones need to be at a certain location at a certain time, right? That control happens from typically a ground station, because it's very unreasonable to expect all of these to talk to each other, right? Even if they do, there will be a reasonably rigid network, which will make sure that these devices talk to each other and the communication between them happens in such a way that this shape that you want is realized within some reasonable time. Okay. Similarly, you can look at a case of a drone rescue where the people who are trying to rescue, the drones are located at different locations in a disaster zone. And the areas where they want to look for life, they may be completely random because there is no way we will know, looking at a disaster zone, where a drone is likely to find a survivor, right? So the drones will be located at different points in a given area. And because they'll be located at different points and we do not know them a priori, you can consider them an instance of a random process. We'll come to that in a minute, right? And similarly, you have air taxis, same story, right? So the air taxis are also interesting because not only do you have vehicles which are sort of moving in a certain convoy or in a certain formation, because that is how they're given the permission to travel by any civil aviation authority, right? In fact, they will also be asked to maintain certain distances and also follow a certain flight path. So not only do we have a set of objects that are distributed in space, but that pattern is moving in time. So think of it as a flock of birds. We have all seen birds, right? they move as like a pattern and they keep moving in time, correct? So and the direction that they're moving is dependent on the approved routes that are given by the civil aviation authorities, okay? So let's try to understand what these mean by looking at a toy problem. So I've reproduced what we had, the picture that we just saw a couple of slides ago, and I try to label it, okay? So you have UAV 1, which is connected to, which can hear base station 1, which is base station 1 is heard as a line of sight. Base station 2 is also heard. Base station 3 is also heard, okay? So now let us ask a slightly different question, right? Suppose the UAV is programmed, just like, for example, all our cell phones, okay? It is programmed to connect to the strongest base station. Makes sense, right? You would always want to connect to a strongest base station. Now the question for the UAV is, okay, if I'm stationed here, I will need to connect to the base station which has the strongest RSSI, correct? So which of them has the strongest RSSI? If you go back to our model, the energy from base station 1 is G1 from the fading, S1 from the shadowing, and R1 to the minus alpha is the distance from the base station 1, okay? And then G2, S2, R2 to the power minus alpha is the RSSI from base station 2, similarly from base station 3, okay? I'm assuming that the powers of these base stations are the same. If the powers are not the same, you can add the powers here also, no problem, right? So the connected base station RSSI looks like a maximum of these 3 numbers, okay? But remember, these 3 numbers, each of them, okay, is dependent on where I locate. Now, suppose you are a network designer, and let's say you are Airtel or Jio, right? You have a question where you want to know, you want to get away by putting as few base stations as possible so that, yes, is there a question?
You are picking up R1 is equal to D11, R2 is equal to D12?
Yes.
Yeah,
Yes.
okay.
Thank you. Good question. Yeah. Okay. So if I were to think like a network provider, I will need to install these base stations B1, B2, B3. Okay. Now, suppose I install these B1, B2, B3. Okay. Remember that when you install these base stations, there are many other considerations which are not only technical. For example, I will need to find land where I'm able to install these base stations. I will need to find power connections that can be used to serve these base stations, and also hook them up with a backhaul. Correct. So all these considerations mean that once I install these base stations, I will not move them. Right. So I found these base stations, the lease site. Okay. I installed it on a building or I installed it on the ground somewhere, and I left it. Now the question that I would ask is, given this collection of base stations, okay, what is the, if I move a UAV around, okay, what is the connected RSSI strength? Correct. Now if I move the UAV around from, let's say, UAV location 1 to UAV at location 2, clearly these distances are now changing, and so are the different fading and shadowing random variables. Okay. So the question that I would ask is, what is the average RSSI, okay, that these base stations can support? Okay. So which means there is some kind of mathematical expectation. This is the expectation that I need to do. But the question is over what? Okay. So there is some expectation there, but I don't know what I will find the expectation on. Okay. Any guesses what I should find the expectation on?
One guess is average, it seems.
Average over what? That's my question.
Of
average
all
over
the
what?
3 RSSIs?
Yes, but these RSSIs depend on the position.
Yeah.
So the position will keep on changing. Right?
Right, sir.
Right? So the issue is because the position is changing, right? I can think of, in this case, you need the fading distribution, because the fading wind can keep changing. The shadowing distributions you will know, but also you need to know the location of the UAVs that you want to consider. So for example, let us say I'm only considering UAVs in this location and in that location. I'm not going to serve UAVs anywhere else. Then I'm going to pick up the average over all these locations, and then the average over all those locations. That is my average connection RSS. Make sense? Right? So if there are more than one UAVs, there's more than one UAV. Let's say there are 3 UAVs in a SWAT. Okay? Then I will need to find the joint PDF of these locations, because all the 3 UAVs are not independently placed of each other, right? They'll be flying close to each other, correct? And they'll be maintaining some distance from each other, correct? So I need to find the joint PDF of these UAV locations also, okay? I'll need that to find the average RSSI. Is this clear? Because this is kind of the bedrock of most of today's session after this. Okay, great. So now with this picture in mind, let us understand whether this analysis or this approach is scalable. Okay. So let's say you have N, which is a swarm, right? You have multiple swarms, correct? Let's say you have 100 UAVs. Okay. And let's say you want to do that, right? You want to still consider the location of these UAVs as a high dimensional random vector, correct? So for example, if you go back to this example, in this case, the number of entries in this random vector is 3. You need to know the latitude, longitude, which is the location on the ground, and then the height, 3 dimensions. So if you have, let us say, a swarm of 2 UAVs, it will need 6 dimensions, right? Yes, please.
So there is a question like a
Yes.
minimum of 3 is required for
Yes.
analysis, right, sir? 2 will
That's what
not
I'm
help
saying.
us.
2 is not enough. 3 is required.
3
right?
minimum
Yeah.
3. 4, 5, and is better for the minimization of errors in estimation.
No. We are not estimating anything. We are assuming it is known. Everything is known perfectly.
Okay, the UAV location is also known.
Let us, even if you assume that, what happens is, if you have one UAV, you need 3 numbers to specify where it is, right?
Yeah. Minimum
Okay.
3 is required.
Minimum 3 is required. What happens is, let us say there are 2 UAVs and they're flying as a formation. Okay. Then you will need 6 numbers, no? 3 numbers is not enough. Correct?
Right, sir.
Correct? Right? So what happens is, if you have, let us say, N UAVs, okay? N is typically 100. Okay. So let's imagine that, there's a large area here where there are 100 UAVs, in some small clusters. One UAV cluster has 5 UAVs here, another 5 UAVs there, another 2 UAVs here, another 7 UAVs there, and so on. Correct? So how many number of UAVs are there? Let us say there are 100 UAVs. That means each UAV requires 3 dimensions, correct? 3 numbers. So you need a PDF which has how many dimensions now? 300 dimensions, correct? Because you need to account for all the UAVs, correct? Right? So this approach very quickly becomes unwieldy, okay? So it is precisely to address this problem that you can think of needing a stochastic process approach. Like this is exactly how, when we teach stochastic processes to undergrad students, we talk about random variables, random vectors. Then we say, let's say the random vector size is infinity. That means there are many numbers in that, not finite number. Okay. In the same way, instead of saying that there is a finite number, let's say 2, 3, or 100 UAVs, I say these UAVs are a realization of a stochastic process. Okay. So each realization of the stochastic process is what I call a point pattern. Okay. So for example, okay, let us say that I have a random swarm size. Let's say the swarm size is random. That means I may have deployed, let's say, N UAVs. N is depending on the mission. Okay. So depending on the mission, N can change. Let us say N is some Poisson random variable. We'll come to this in a few more slides. Okay. But suppose you have N, which is a Poisson random variable, and you're deploying all the UAVs at some height 100 meters over a city neighborhood of size 1 kilometer by 1 kilometer. Okay. Then those UAVs will look like randomly placed UAVs, which are there in this 1 kilometer by 1 kilometer radius at a height 100 meters. Okay. So this is how it looks, for example, right? So one other example is, if you take a 5G network, like a cellular base station network, correct? And you plot where the base stations are, right? I found this on one of these websites. So I took two places. One of them is in Cupertino, where I used to live. Another place is in San Jose, okay, where I used to work. Okay. So both these places, if you see the red dots here, they constitute the locations of the towers. Okay. So if you notice, they almost look like they're along the roads, but except for the fact that they're along the road somehow, the dots don't seem to have a nice hexagonal kind of pattern that everybody teaches in textbooks. Correct? So if you go to open any wireless textbook, they will say hexagonal cells are the most efficient, correct? And they'll give you this 120-degree sectoral antennas and all that, right? But this is real life, correct? This is actually data that is gathered by companies, right? Same thing happens with San Jose, right? So you have two such instances, and you can pick the same thing up for any other city where it's available. I'm pretty sure Hyderabad or Warangal will be very similar. Okay. Now, the point I'm trying to make here is, just like we imagine, okay, a random variable to take many numbers, many values. For example, if there is a uniform random variable which is between 0 and 1, it can take any value between 0 and 1, right? It can take a value 0.1, 0.2, 0.12, 0.61, so on. So in the same way, we can treat this point pattern as a realization of a stochastic process. Okay. So that is the intuition, that main intuition that you should carry away after this course. Okay. So, and yes, please. Yes.
Point process.
Yes.
They are IIDs.
Not necessarily IID. Very good question, sir. But it's not IID. Yes.
Okay. So the arrival of each point is independent of the other point's arrivals.
Not necessary. Not necessary.
Okay. So generally, because when we try to model the telephones and all, we use the arrivals as Poisson arrivals only, because each call is independent and they don't depend on the previous call.
Correct. Correct.
So it is something like that, or no? Nothing to do with it.
So this is a very, very important and very insightful question. Okay. So I will answer probably 50-60% right away. Okay. The remaining ones we can as the slides go on, we'll do it, and I'll definitely come back to this question a lot more detail towards the end of this talk. But first, let me start answering this question. In the case of telephone networks, when your call arrivals are considered, Poisson arrivals, okay, as the professor rightly said, it is because basically that you can think of these call arrivals as an aggregate of many, many smaller arrival processes, correct? And the overall process will look Poisson because one arrival is independent of other arrivals, basically, correct? That's the intuition, okay? Now, in a case of a spatial network, there is no concept of a time, isn't it? There's no time here. There's only space. You took a photo and that's it. Okay. At any given time, you took a photo. Okay. So in that case, the counterpart for this kind of randomness is what we will call a spatial Poisson process. Okay. So you can define, just like you said that the arrivals are independent of each other, the probabilities of finding a point in any small, just like in an arrival, what happens is, if you break up time into very, very small chunks, in any small chunks, either there's an arrival or there's no arrival, okay? And between two disjoint chunks, you cannot say anything about, just because an arrival happened in one of the small chunks of time, you cannot say anything about whether there's an arrival in the next slot or not, correct? That's what is basically called memorylessness, correct? So that is basically how this Poisson property comes in, right? The same property
really good
taken in
that actually visualizing that is really required at this stage, because otherwise we take time as the arrival rate and then it will land up in some other
Yes. That's why I was about to, I had some slides on that.
Okay, sir.
So
thank you.
So what I wanted to say was, think of, instead of taking time as your arrival thing, okay? Imagine that you had space as the point where you can place these dots. So imagine, for example, right? Let us say you're going on a plane, okay? You have a lot of these sort of small mines or pamphlets or whatever you want to call them, okay? And you drop them, okay? Do you think they will fall just because one particular mine or one particular sensor fell at one location? Do you think it will have a bearing on where other sensors fall? What is the intuition here? It should not depend, correct? It should not depend, right? that is exactly the intuition that one should have for a spatial point process. Imagine that these points were thrown by somebody from a plane. Okay, they fell uniformly, randomly throughout the circle that you see here. Imagine that. Okay, they fell uniformly, randomly in this circle. Okay, now imagine that the number of points you're throwing is some Poisson distributed random variable. That much is easy to understand. Okay, suppose I gave you one Poisson distributed random variable which has, let us say, mean of 10. That means on the average you'll throw down 10 points. Okay, but once you decide on how many you want to throw, those points will be distributed uniformly, randomly, independent of each other. Is that is that creating a good intuition for a Poisson process? Right? Right. So that's a spatial Poisson process, correct? Now it is no more dependent on time, correct? It's a spatial process, correct? In space, correct? It's not in time. Not in time. Okay. Now I must give a caveat here. These processes are definitely not Poisson. Why? Because you're not throwing them uniformly at random. You're only throwing them along the roads. No? Right? You're throwing them close to houses. Correct? So in reality, these Poisson models, they may not be 100% fit. Correct? If you think of this as data that is from the field data versus analytical data, it's not 100% fit. Okay? So for example, even here you'll see, right? In San Jose, this area happens to be what is called the downtown. Okay? So there's a lot of offices here. So there's a lot of density in places where, there are people. Okay? And there's low density here, right? So all those things we'll look at. But the basic intuition I want to give is there is a point process which you can create. Just like you create a realization of a random variable, you can create a realization of a point process. So let's understand in the context of UAVs. It becomes even more interesting in the case of UAVs. Okay. So let's imagine that you're trying to build a traffic management system for unmanned systems. This is a very important point. Okay. And what happens is when you want to deploy UAVs, there will be regions where the UAVs cannot operate. Like, for example, there may be high security areas where you don't want drones, like airports. Okay. And when they do operate, they need to operate along certain paths, correct, on these roads that you see here. Thirdly, even when they operate on that road, they need to have a safe separation distance. Why? Because they don't want to collide into each other. Okay. So what happens is you will end up having a point process in aerial networks where not only are you having 3 dimensions, you have lat, long, and also the height, but also you have regions which are forbidden. Okay. And also you have the safe separation distance, and you also have deployment along certain paths, not everywhere. Okay. So all these things mean that you can actually think of point processes for various types of deployments, not just on terrestrial. You can think of aerial deployments also as needing some kind of modeling like this. Okay. Right. So just to reiterate what you said, I want this picture to be sort of very firmly in our minds, right? So we are all aware of how random variables are defined. Random variables are basically maps from an outcome, right, from a sample space. So you have omega, which is your sample space, which is a set of all possible outcomes. Okay. And you have a random experiment where you pick up an outcome randomly. And depending on that outcome, you're given a particular value. So for example, if this capital X is a uniform random variable between 0 and 1, then this X of omega 1, X of omega 2, and so on will all lie between 0 and 1. Okay. So that is one way to think about it. Every time you have a particular realization, let's say 0.12, X1 is equal to 0.12, it means it is due to some omega 1 that resulted in the random variable taking a value 0.12. Okay. So this omega 1 you can think of as chosen by nature. Okay. It's not in our control. Right. In the same way, if you take a point process, just like you have a random variable for your X, right? And here we're calling it a point process, which is phi. Okay. And phi of a particular outcome will result in a point pattern. Okay. So for example, if I take omega 1, let us say picks up Cupertino, omega 1 picked up small phi, which is this point pattern. Okay. Omega 2 picked up this particular point pattern. Okay. So these are two realizations of a point process, just like these two are two realizations of a random variable. Is this kind of making sense? Good. So there is some nuance here, which I am deliberately not going into. There is what is called a sigma algebra that I need to define, okay, on omega, okay. That requires us to go a lot more into the math, but I would really encourage you to see the references that I mentioned, okay. There are very good resources where if you want to understand this much more, all the nuances and the technicalities I've mentioned there, okay. But for our purposes, this much is sufficient to kind of understand, okay. Right. So therefore, we are now in a position to define. Yes, please. Yes, please. Yes, please. Yes. 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 Excellent question. Excellent question. Excellent question. It is, you can think of it as a process which is both in space and time. So it's basically a 4-dimensional random process.
Yeah, it's becoming
right?
Too much complicated.
No, it's not that complicated, because what you can do is define an operation on one realization of a random process. Yeah. Okay. Yes. Suppose, as an example, just to make it very simple, imagine that there's a line of cars. Okay. Yeah. Right. And the line of cars is moving, let's say that the distance between cars is 10 meters. Yeah. Okay. And there are 10 cars. Yes. Okay. Now imagine that the cars are traveling at, let's say, 30 kilometers an hour.
Constant, homogeneous.
Homogeneous. Then what will happen? This pattern has moved from one place to another place. That's all happened. No, they're going on a straight road. Yes. Correct. Right. So what you can do is imagine that the point process you can imagine it like a video, right? At each snapshot, it's a spatial point process. Individuals, and you stitch together all these snapshots, you get a time point process. Correct?
It's like a motion.
Like a motion, like a picture, like a movie. Correct? Exactly like a movie. Yeah, yes. Correct? Right? So it's not that hard. You just need a model for how they move. Okay. Right? Okay. Yeah? Thank you. That's also described very well in a lot of literature. Okay? Right. Okay. Very good question. Okay. So, so now we are in a position to define what is formally a point process. Okay. So again, there will be a little bit of terms that I have highlighted here, but we'll go through them. So a point process is a countable random collection of points. Why do I say countable? You can give a number. It is some natural number. There are no points, 1 point, 2 points, 31 points, 127 points, 1001 points, whatever. Okay. So there's a countable collection. It's a random collection because the locations of these points are not known ahead of time. Okay. They are points in the real space. So d-dimensional real space. Okay. That's a standard notation. And the number, such that the number of points in any Borel set B, okay, I'm going to call it phi of B. It is a random variable. Okay. So what it means is, if I take imagine, let's say Borel set is a rectangle. All these are Borel sets. We'll come to it in a minute. But imagine that this is a rectangle. Okay. If I take this rectangle and I fix that rectangle on, let us say, R2. Okay. Each realization will put a different number of points in that rectangle. Okay. Therefore, the number of points is a random variable. Okay. Right. So now what is a Borel set? Okay. So technically, if you want to say precisely what it is a Borel set can be written as a countable union intersection or complements of open sets. Okay. So countable means you can actually say that, you can assign a natural number to it. So you can say there are, five unions or 6 unions, or you can say countably infinite, or you can basically, it's a countable operation. Correct. So I don't want to say anything more than that because it will drag us too far away. But one way you can think about it is, any Borel set, you can actually chop it up into smaller, simpler sets. For example, take this rectangle. I can chop up this rectangle into very, very small rectangles. Correct. And each of the rectangles, I can chop it up into very, very small rectangles and further. So I can represent this big rectangle as many, many smaller rectangles which are non-overlapping. Correct? Union of all those smaller rectangles which are not overlapping. It's more like a mesh. Imagine that I put a mesh on this rectangle. Okay? The same thing applies to a triangle. Yes, please.
So it means that a rectangle can have subsets of rectangle, or it can be any other
Yes.
geometry.
It can be any other geometry.
Okay.
I'm giving one way to visualize it. Okay? So you can, typically what you do is that if you start with these open sets, one way you start with open sets is intervals.
Yeah.
Okay? 2, 3, open interval 2, 3 is an interval. Okay? Similarly, in 2 dimensions, a square whose sides are not included is an open set. Okay? So what you do is, if you want to show something as a Borel set, you take these more elemental sets. Okay? And you show that you can use those elemental sets to create this big set. So for example, let's say this one has length 10 and this one has breadth of 2. Okay? You can now create, squares, smaller squares here, right? Yeah. It's like a mesh. Okay? And so on.
Okay. Okay, sir.
Okay?
Thank you.
Right? So the same thing applies for a triangle. Okay? Why am I saying it applies to a triangle? Because I can take any triangle, I can break it up into, I can approximate the triangle to any degree I want using a finer and finer mesh. Imagine that you have a square mesh. Okay? The finer I make the square mesh, I will count only the squares inside this triangle. Okay? Are you kind of intuitively seeing that if I make the mesh finer and finer and finer, I'm going to get the set of the squares inside this will be approaching this triangle. Right? So what we are trying to say is that you can approximate this triangle to any extent you want using a very, very, very small squares. You can think of it that way. Okay? So the same thing applies to this star, same thing applies to this oval, same thing applies to this weird shape that I drew here, and same thing applies to this infinite half plane. Okay? So all the nice shapes that we can draw with hand, okay, and the shapes that we care about, they're all Borel sets. So for our practical purposes, this technical requirement is met. You don't have to worry. Okay? But to be technically accurate, you need to describe it in this way. Okay? So you can as well say for any set that we care about, okay, of importance to us in practice, right? The number of points in that set is a random variable. Is that kind of making some sense? So if I pick up, let us say I pick up this oval, okay, depending on whether that realization puts, a particular realization may put 2 points in that oval, it may put 5 points in that oval, or it may put 100 points in that oval. Correct? It's a random collection of points. Right? This clear, I want to move to the next point. Okay. So the one small thing I want to mention here is a concept of what is called a Lebesgue measure. I'm not going to go deep into Lebesgue measure, but all I'm going to say is it is like the volume of a set. So for example, if you say that this B is a line segment in real numbers, mod B is basically its length. If B is a circle, let us say in R2, then mod B is the area. If it's in R3, it is the volume. Okay? So imagine that it is just the volume or area or length, depending on the dimension. So I'll use the term volume without losing generality. Okay? So if I have a volume, that volume of that set is what is called the Lebesgue measure. Okay? Technically, that is what it is. Okay? Make sense? Yeah. Okay. So now we are ready to tackle the first point, set of things, where we define a binomial and a Poisson process. Okay. So first, let us understand what a binomial point process is. Okay. So imagine that you have a set of n random variables, x1 to xn. Okay. All of them are d-dimensional. So you can assume, for example, there may be UAVs, right? So d is equal to 3. Okay. And you have n is equal to fixed. So let's say you are modeling the locations of the UAV's form. Okay. So if you have a UAV's form, which has, let us say, n elements in it, okay, n UAVs in it, each of these xi's is independently drawn from some PDF. Okay. So why would you sort of model something like this? So for example, let's say you have a UAV where you know how many swarms, how many points, how many UAVs you deployed already. Okay. But you want to model where they are located. Okay. So you know how many there are, and that's never going to change. But you want to know where they're located. Okay. So one place you can start with is assume that each of these XIs are independently chosen according to some PDF. Okay. So this is one example. So let's imagine that you have 1 kilometer by 1 kilometer neighborhood, okay, and I'm seeing from the top, okay. So you have, let us say, a UAV swarm which is 30 UAVs big, okay, and they're uniformly randomly deployed in this neighborhood, which means I take each UAV, I put it uniformly somewhere between this square, right? This is like a unit length square, right? 1 kilometer by 1 kilometer square. I put it randomly in the middle somewhere, okay. Each of them I put it independently of the others, right? So this is one such realization of what is called a binomial point process. Okay, it's a very simple process. You can equivalently even think of it as a random vector, correct? In this case, you can think of it as 30 UAVs. Each of these UAVs is, let us say, located in a 1 kilometer by 1 kilometer, which means that you need how many total dimensions to describe all the UAV positions? How many numbers? 30 times 2, correct? And if you also assume height is different, you need to assume 30 times 3, right? Each of them requires 3 dimensions, right? So, but we have avoided that problem by simply converting this, the 30 dimensional or 90 dimensional PDF, we got rid of it and we said, let us have a point process, okay, to denote where these UAV locations are, okay, right? So I want to give a flavor for why it's called binomial. So it seems very arbitrary that you should call something like this binomial, right? So let's start with, like a very basic idea here, okay? Let us say that you have some W, which is where you deployed your swarm, okay? And you have some set B, okay, within strictly inside this, or at least contained in this, okay? Now, what is the probability that I'm going to have exactly K UAVs in B, okay? Okay, it turns out that can be written as the binomial distribution. Okay, so that is why it's called the binomial point process. So for example, in this case, this W is given by this oval outside egg-like thing. The B is the inside thing. And I took one realization of 5, correct? So in this one realization of 5, how many points are there? There is 1, 2, 3, 4, 5, 6, 7, 8, 9. There are 10 points, okay? And it turns out that this particular realization of 5 put 2 points inside this, okay? Some other realization of 5 may put more points inside this or less points inside this. The probability that the 5 puts in exactly K points inside this is given by this particular distribution, binomial distribution, okay? So, is it clear? Yeah. So what we say is, here this small p has an interesting interpretation. It is a probability that any given X is inside this B. It is nothing but the PDF of X integrated over B. This is basically your BTech material, correct? So if I'm given the position of any one of these UAVs and it has some PDF of f of X, if I integrate that over B, that is a probability that X will be inside B, correct? And because this is chosen, all the X's are chosen independent of each other, probability that K of them will be inside B will be P to the K, okay? 1 minus P to the power N minus K will be outside B. And because I can choose the K of these UAVs in N choose K ways, I get the first factor, standard binomial distribution, okay, right? So in particular, if this PDF is uniform, that means I'm uniformly randomly putting a point inside W, then this P becomes what? If I plug in 1 over W here, it will become constant. So this becomes integration over B of dx. This dx is in this case, it is the area element. In general, it is a volume element. Okay. So integral over B of a volume element will be the volume of B divided, therefore, the f of X is 1 over volume of W. So it's P is volume of B by volume of W. Does it kind of make sense? Yes, please. Yes, please. Yes. You can think of area by area also. You can even think length by length also. You can define binomial point process on a line. Yes, line by line, area by area, by volume, no problem. There was another question. Was it you, Professor, or somebody else? Yeah. Yes. So it depends on what space this is in. If this is in three-dimensional space, then this W mod W will become volume. Yes, depending on the dimension in which this process is there. So, for example, let us say you are trying to deploy UAVs within a region which is, let us say, between 100 meters and 200 meters in height. Okay. And over a 1 kilometer by 1 kilometer area, correct? So it will be like a slab, its thickness 100 meters. Okay. Length and breadth of the slab are 1 kilometer by 1 kilometer. In that case, W will be that slab, correct? No? Yeah. Okay, good. So let me go back. Okay, right. Okay, so now we are ready to look at what is a Poisson point process. Okay, this is exactly the thing that the professor was asking in the beginning, and we'll go into a lot more detail here. Okay, so I'm giving you the formal definition, which is that if you take any Borel set, which is basically a set which you can nicely approximate with some nice other sets like we discussed now, okay, and any set B I take, okay, which has a finite volume, okay, the points are distributed using in a Poisson way, where the parameter of the Poisson random variable is some parameter which we will call lambda multiplied by the volume of that area, volume of that space, correct? Volume of that set, correct? So for example, when you see that, let us say B is, let's say 1 kilometer by 1 kilometer area, okay? So the mod B will be 1 kilometer square, correct? Right, area, okay? And this lambda is what is called the intensity of the point process, okay? So if I'm given a B, which has some bounded area, okay, I'll first find the number of points which the process will put in B. It is a Poisson distributed random variable whose mean is some intensity lambda multiplied by this area, okay? If it's 3-dimensional, this thing will become volume, okay? The second point is important, is that if these points B1, B2, and so on are disjoint, then the number of points that the process puts in phi of B1, number of points in B1, number of points in B2, and so on, they're all independent random variables. And that is a very important property of the Poisson process, okay? Just like, for example, in a one-dimensional case, if you have two intervals of phone call arrivals, okay, the number of arrivals in two disjoint intervals are independent of each other. Am I right? Right? So in the same way, the number of points within two disjoint regions of space are independent of each other. Okay? It's exact analogy. Okay? So because we assumed it's a Poisson distribution, the probability that the number of points in B is exactly n is given by the standard Poisson distribution formula. Okay, this is just the Poisson formula. Okay, one interesting thing about PPP is that it can very easily be used to define point processes on potentially unbounded sets. Okay, so you can, for example, think of, let us say the points in a base stations in a city. Let's say you have a very big city. Okay, sometimes it makes more sense to think of a very big city as essentially infinite, correct? It's easier to model mathematically to take a very big city as potentially the XY plane. Similarly, if you have any UAV deployments on this very big city, it makes more sense to think of the centers of those UAV clusters, okay, as potentially coming from a Poisson process, correct? because those centers can be all over the city, right? In much the same way, the cell phone users in the city, okay, are also, you can think of them as Poisson, because you're thinking about a very large area. So anything where you have very large area or volume, you may want to consider, a Poisson process, okay? You can also consider a Poisson process on a bounded volume, okay? This is not saying that you cannot consider Poisson process on a bounded volume. You can also consider Poisson process on a larger volume also, okay? So that's one thing, okay? And the next point is that if you know, and this is where the airplane example that I gave to the professor is kind of tying in. If I know that a given area has endpoints, somebody told me that I know that there are endpoints, but I don't know where they are, okay? Then, if the process is a homogeneous Poisson point process, then all those endpoints are uniformly randomly distributed in that B. In other words, if I know that the Poisson point process put exactly endpoints in a given neighborhood, then those endpoints form a binomial point process of order n with a uniform PDF. Okay? So this goes back to the airplane example where we said that when you take an airplane, you decide the number of points. Okay? Let's say you decide the number of points to be some Poisson number of points.
Can we define like that? Like if I have uniform distribution,
Yes.
Hello? So, you full screen. Okay. So, I think before we took this break, we were looking at how the question that the professor had was, how is it a binomial point process, right? So, where the number of points is fixed as n. There's no randomness there, okay? Once you fix the number of points, each point is independently drawn according to a common PDF fx, correct? So it's basically saying that I have n independent identically distributed random variables, okay, which have the same PDF f, okay? So n independent identically distributed random variables and n is fixed, of course, right? Now that constitutes binomial, right? That is BPP. What we are saying in the case of PPP is the number of points that the PPP puts in a given ball or a given area can be different, correct? It's distributed according to this. But given that it put n points, okay, given that it put n points, those n points, each of them, their locations do not influence each other.
Yes.
Correct? That is why they form a BPP of order n. It's order n because there are n points. We are already told that there are n points.
Yes.
Okay?
Correct.
And in this case, the BPP, the common PDF that you are trying to sample is 1 over B, which is uniform in the area that you are interested in. So for example, if your BPP, if the B is a square, okay, of length 1, then what you're saying is, given that there are 5 points in that square, those 5 points are independently drawn uniformly randomly from that square.
Right.
Now it's clear?
Right, sir. Right.
Given that there are 5 points, they are uniformly randomly drawn.
Yes.
Okay, that is okay. So this condition is important to understand that fact. Okay.
Right.
So
thank you, sir. That is good. Okay.
Yeah. Okay. So,
Sir,
just
can
to,
you put your
yes,
video on, sir?
sorry?
Video on.
Oh, yeah, sure. Yeah. Let me
Right,
go
sir.
back.
Okay.
Yes. Okay. View. Yes. So, okay, this is what we call the homogeneous PPP. Okay. So, reason I'm emphasizing the word homogeneous is there is something called non-homogeneous. We'll come to that in a couple of slides. Okay. Now, if I were to look at different realizations of a PPP, how would they look like? Right. So, let us say that I'm interested in a homogeneous PPP over over a region W, which is basically the unit square. 0, 1 is interval 0, 1. 0, it's a square. Okay. So I took lambda equals 10. The intensity of this process is 10. Now, you see two realizations from the same process. One realization I'm calling small phi 1. Small phi 1 of W is the number of points that small phi 1 puts inside W. That means the number of points in the square. In this case, it is 14. Okay. But small phi 2 of W is 9. Where is this randomness coming? It's coming because the randomness in the number of points. Okay. Because the number of points is Poisson distributed with parameter lambda, which is 10. 10 multiplied by area of W. Area of W is 1. So n, the number of points, will be a Poisson distributed random variable with mean 10 or with parameter 10. Okay, so this is different from a binomial point process, where in binomial point process the n is fixed always. Here n can change. N itself is a Poisson random variable. Okay, so that one point I want to emphasize. Yes. So the way, yes. Yes. So the way I would look at it is there can be many scenarios, right? One scenario could be, remember that when you're averaging over different realizations of a process, you can even think of different realizations as coming from different missions that the drones are executing. So there is no reason why you should assume that a fixed number of drones will always be deployed for a given task. Right? That's where your randomness is coming. Right? Yeah. Okay. Any other questions before we move on? Okay. Okay. Good. If they are happy, I'm happy. Right. So this is a good time to generalize what we saw and consider what we call a general PPP, okay, or a non-homogeneous PPP. Correct. The way it's defined is like this. Okay. So this is a technical requirement. You want it to be bounded, of course, and you want it to be closed. Okay. So this bounded and closed set is what is called a compact set in mathematics. I didn't want to go like technicalities, but basically imagine a nice set. Imagine a nice ball. Okay. Or imagine some nice shape that you feel is bounded. Correct. Like some deployment area in a city, or some region in space. Correct. That you can bound nicely. Okay. And it has a finite volume. Okay. The difference is I'm allowing the number of points in this B to be Poisson distributed according to some intensity measure, okay, or a mean intensity measure lambda. Okay, I will use a slightly informal term. I'm going to call this capital lambda of B. Okay. Now the difference between the homogeneous case and non-homogeneous case is, for the homogeneous case, this capital lambda of B is proportional to the volume of B. That's all. Here, it is not only the volume of B, but it also depends on what that entire set B is. Okay, so which means it doesn't have to depend only on volume, it may depend on other things. Okay, so in most cases of interest, you can write this capital lambda of B as an integral in terms of something called the intensity lambda of X. This X, by the way, is d-dimensional. This is not like a one-dimensional. This X is a d-dimensional vector, correct? So this dx is a volume element. Okay, so yes. So it's called the intensity measure. Okay, So this is called the intensity is basically lambda of x. Okay. So when the process is homogeneous, then you have lambda of x is constant, in which case this capital lambda of b is lambda times mod b. Okay. Right? Okay. The interesting thing is, even with this kind of a change, the second point, which is that when you have disjoint B1, B2, B and so on, the number of points phi of B1, phi B2 and so on, those points are all independent random variables. This feature is also shared if you go back to the homogeneous point process case. It's also shared with the homogeneous case. Okay. So this problem is coming because of memoryless. This property is coming because it's memoryless. Okay. And this memorylessness fundamentally comes from this Poisson property. We will not go into that here. We are treating it as two separate things, but actually this property actually implies this property. Okay.
Right? So again, in statistics also we teach like that only.
Yes.
The set is separated.
We separate it out, but actually one property follows from the other property.
Yes.
Okay. Right. I think it came in 67. I think Rennie proved it. Anyway. But anyway, once we are done with this, okay. Remember we said that given that the number of points inside B is n, the points inside B form a BPP for the case of homogeneous case. For the non-homogeneous case also they form a BPP. But now this f of x is not uniform, but f of x is given by this formula. Okay. It is lambda divided by integral over b of lambda. Okay. So you can think of this integral over b of lambda as some kind of a normalization thing, because if you integrate over b of fx, this will become 1, because the numerator will become 1, denominator is still integral over b of lambda x, right? So this is basically a normalization term. So you can think of one intuitive way to think about Poisson processes is that if I am given some intensity lambda of x, okay, the probability of finding a point in a small volume around x is lambda of x times dx. Okay?
No.
Right? Probability of finding one point. Probability not finding any point is 1 minus lambda of x dx. Okay? That's a very heuristic way of thinking about it. Okay?
Yes.
And if I pick disjoint volumes, okay, the number of points in disjoint volumes are independent. Okay?
Okay.
The same reason as this case. That disjointness carries over to collections of these small delta x's, bigger volumes also. Okay?
Correct.
Right. So just to give a flavor for how rich this formalism is, you can actually take all kinds of choices of lambda. So I've taken, for example, a two-dimensional case. Okay. And what I did was I took x1 is the x-axis, x2 is the y-axis. Okay. So what you see here is one realization of a point process on 0, 30, which is your x-axis, 0.5, 4, okay, on the y-axis, okay. And the intensity along the y-axis is decreasing. That means there are not many points coming up in the vertical direction as you go on. Whereas along the horizontal direction, it is sinusoidal, which means the intensity comes down, goes up, comes down, goes up, right?
Yes.
So you can create all kinds of interesting patterns which are not very trivial, correct? So you can do, for example, something even more funny, right? You can try to make it a completely periodic thing. So you can keep some clusters of points which are created at regular intervals. So you can think of them as, let us say, swarms of drones that are created in these places, for example, right? So you can kind of work with some of these models to actually build a more realistic framework. And you can actually take a Poisson process and you can modify it to create new types of processes. Okay. Yeah. So we won't have time to go through it. I'll just point you to what can be done, and I'll give references for that. But basically, it is somewhat very analogous to how white noise, okay, yeah, is used. Okay. So I will come to that in a minute. Right. So what are the key properties? The first thing is the number of points in disjoint subsets are independent. Okay. And this applies to all PPPs. It doesn't care whether it's homogeneous or otherwise. Okay. The interesting point which is used quite heavily in a lot of work is that it is stationary. Okay, what it means is, if I take a homogeneous point process over the plane, over the entire plane, or the entire R3 over the entire space, okay, I can move the origin of that space to any point I want, okay? So I can take all the realizations and say I've changed the origin point to some other point, okay? If I look at the realizations, I cannot tell the realizations where I've changed the origin from the realizations that have not changed the origin. Basically, if I take, let's say I had 1 million realizations of this homogeneous point process over, let us say, R2, I shifted the origin, therefore all these realizations will be shifted, correct? They'll look differently. But when you look at statistically, that new ensemble of all the realizations with the shifted origin, it is no different from the original ensemble. Okay, that is stationarity.
So
correct?
the patterns are
isotropic refers to the fact that it does not matter which direction I rotate the along the origin. Okay, so right.
The swarm is constant, but you are shifting the swarm to one point to other point.
Yeah. So what I'm saying is, if I take a big city, if I'm in a big enough city, it does not matter where I choose my origin in the city, because the city will look the same around me.
Yeah.
Correct.
So now I can move that in whatever pattern I want. The origin only.
So you're allowed to translate the origin.
Origin only I can move around, but the pattern around the origin will move as it is. There will be no change in that.
No. So the patterns are there in space.
Yeah.
We are choosing a particular origin to measure where they are.
Yeah. Okay.
The patterns are now fixed. Okay. Let's say you took a pattern of points.
Right.
Okay. And now you say, let's say this pattern of points is there all over space. So for example, let us say it's all over R2. Okay.
Yes.
All over the XY plane. Okay. You shifted your origin from 0, 0 to, let us say, 1000, 2000. Okay.
Yes, sir.
It does, even if you sit at 1000, 2000, that process will look the same to you all over the space. Basically, there is no difference in how the process will look to you, whether you are sitting at 1000, 2000 or 0, 0.
Right.
Statistically speaking.
Yeah, right.
Right? So we'll see a concrete example in just a bit, right? The other thing is isotropic, which is when you rotate around the origin, the property should not change. Okay? So if you have something which satisfies both stationarity and isotropic property, it is called motion invariance. Okay? Okay? Non-homogeneous processes are not motion invariant. So I'll give a solid example why this is non-stationary. So if you take this example, okay, you will see that if I'm sitting at 0, the crests and troughs are at this point, this point, this point, and this point. But suppose I move the origin to, let us say, 10, okay? Yes. The crests and the peaks and valleys are now different, right? They are now differently located. No? If I'm sitting, 10 is my new origin. Right?
Yeah, right.
Right? Similarly here, if I move this origin, let us say from 0, 0 to, let us say, this point in the middle here, okay? This point, the process will look different for me.
Yes.
Right? So these processes are not stationary. Okay? And of course, they're also not isotropic, correct? If you rotate it, it'll look different. If I rotate this, let us say to 45 degrees.
So then we can, how can we define stationarity in that case, sir?
Exactly. So so stationarity is defined as the property where the strictly speaking, the distribution of the process is invariant to shifts in the origin. So if I look at the set of all possible point patterns that constitute a PPP in space, okay, and I perform a transformation where I move the origin from 0 to, let us say, some R0. Yes. Okay. So all these point patterns will now be, they'll be the same, but they are now referred to R0 as a new reference, correct? If I take the R0 as a new reference and then I ask any property of this point process, this ensemble, okay, the properties will remain the same. Right? So there is a stationary.
If the points are stationary.
Exactly. Just like stochastics, the standard time. In time domain process, we talk about stationary process.
Yes,
same concept. Yeah. Okay. So, yeah. Okay. So what I want to now touch upon is the last part of my talk, is that we have just touched upon like binomial and Poisson, right? Which is like basically the most basic processes you can think of. The one point that is used very often in the stochastic geometry community is this notion of an ergodic process or ergodicity, okay? And it turns out it has a very important engineering value, okay, which I'll mention in a bit, right? So I think, are the audience familiar with ergodic processes in time? Like stochastic processes which are ergodic in time? Yes or no?
Yes. Can you repeat the question, sir, once more?
Is the audience familiar with ergodic processes in time? Stochastic, like where you can have time average is equal to ensemble average.
So they say yes, sir.
Yes. So in much the same way, if you take ergodic process in time, you are talking about averaging out, let us say, finding the sample mean in time is equal to the ensemble average, right? Yeah. In much the same way, a spatial point process is ergodic. If the statistical properties, if I keep on taking a spatial average of those properties, okay, they converge to the ensemble average. Okay. So in one, if you want to remember it as one sentence, if I take one realization of a stochastic process, okay, it essentially represents the entire ensemble in a statistical sense. I don't need more realizations to find averages. I can use that one realization to find everything I want.
It's a differentiation of the points.
It depends on distribution of the points, correct? That's how the points are distributed.
Yeah.
Correct? Right? So you can see clearly that ergodicity by definition requires an infinite number of random variables. You cannot live with finite dimensional ergodicity. It doesn't make sense.
Yes.
Okay? So we'll see an example, a very concrete example of what I mean. Okay? So let's take a single like homogeneous PPP realization. Okay?
Yes.
And let us say I want to find the intensity. I want to estimate the intensity. Okay? What I will do is I will take small pieces of this process.
Yes.
Okay? Let us say I pick squares of 4 by 4 each. Okay? And I tile this process. I take 4 by 4 squares in this whole area. Okay?
Yes.
In each 4 by 4 square, I count the number of points. Okay?
Yes.
And then I find the histogram of all the points I found. Correct?
Yes.
Then I divide by 4 because I'm finding intensity. I'm dividing by 16.
Yeah.
Correct? Right? So if I divide by 16, okay, what I'm seeing here is the true intensity is 10. Okay? But the rest of the intensities are not very far away, 8.5 to 12.
So,
correct?
Can we approximate to normal again?
This normality will be there, but more importantly, in addition to this normality, the convergence to this mean is critical.
Yeah, that's true.
Right? The average intensity, I can measure it even by taking this averaging over different pieces of a single realization. I don't need more than one realization. Okay? I just need a large enough number of squares. That means large enough area. Correct? So what is happening basically is, in a subtle way, the process is exhibiting the properties of all the processes in one single realization.
Yeah, that's
all right. Somewhere it is going in like that, right? That is why you're able to do all this averaging and come to expectation without taking more realizations of the point process.
This is almost natural for all. Like even in a class, if we conduct exam, the average will pick up.
Yes. So if you go back to like a non-homogeneous process, it is not ergodic. Okay. Why? Because if I try to do something like this here, okay,
Yes.
I will not get the intensity because it's not time average. This spatial average is not the ensemble average. Okay.
Yes, sir.
So what it means from an engineering standpoint is that I can now take I can take an ensemble average and interpret it as a spatial average.
Yes.
Which means if I have a collection of, in a large wireless network, I have many links. Each of the links, let us say, is operating at some bit rate. Instead of, by using stochastic geometry and finding ensemble averages, which can be done more efficiently using analytical methods or some numerical methods, I can find the spatial average of all the bit rates of links in a network in one shot.
Yes.
Okay, thanks to ergodicity. Okay. So that interpretation gives rise to what are called meta distributions, which can also be discussed at a later date. But basically, this ergodicity actually plays a crucial role in tying a lot of stochastic geometry to practice in this sense, because you can take a single realization, let us say deployment over Warangal city, okay, and I can say that the spatially averaged values that I get, okay, will be the same as the ensemble average I get with the simulations. So therefore, I can say something for a person who has actually deployed a specific realization of the network. They cannot change the realization, right? They cannot change the base station locations, for example, right? But you can say something about what they are going to see in an average sense.
So can we say something like, if we take uniform distribution, it can, the average can be at the middle of that, and for other distributions it will not match?
Uniform is one thing. The thing about ergodicity is it requires a little bit more than uniform. Okay. So it boils down to, if you go back to stochastic process, it boils down to what is called a measure preserving dynamical system.
Oh, yes, sir,
so it goes a little too deep into it. But basically what is happening is you are somehow sampling the entire sample space in that single realization.
Do it has with variance also, or no? Only ensemble is sufficient.
So you can now define ergodicity in what sense also. Okay. So you can define what is called ergodicity in the mean square sense, ergodicity in the almost sure sense, and all. Okay. Right. And you can now define ergodicity in just expectation of the number of points, or you want ergodicity in terms of the variance, like you said, right? The variance of the points is also the same, right? Okay. Right. So you can define all that also. Yes. Okay. Yeah. Okay. So good question, right? So this ergodicity is something that we want to sort of use, in our real real world, right? So I want to leave you with one final comment, which is relevant if you want to dig deeper into this. So if you remember, if you've taken any stochastic process course, one of the sort of standout results is that you can take a white noise process and you can create any process which has these correlation properties, like regression processes, right? You pass it through some filter and you'll get some process, correct? So you can create any autocorrelation function you want using a white noise process and some filtering and some processing, correct? In exactly the same way, you can take a Poisson process, okay? And you can take a homogeneous Poisson process and you can create all kinds of other types of processes starting with this homogeneous Poisson process as a starting point, okay? So, for example, just like in white noise, you can induce correlation. Here, you can induce correlation by having points stick together or points repel each other. So this goes back to the question that the professor was asking some time back. How do you ensure clustering? The way you can ensure clustering is you can basically take points. Let's say you take a Poisson process and around each point you draw a small ball and you put more points around the ball. I think Taiba will have a demonstration of that. Yeah. So that you can now model swarms of UAVs, for example. Okay. Or if you want to create repulsion, you can actually create what is called a hardcore process by essentially, ensuring that no 2 points in this original Poisson process which are less than a certain R are retained. Okay. So then you can create basically like a sense and avoid kind of a system naturally in a Poisson, using a Poisson process. Okay. So, and you can also model, for example, things like carrier sense multiple axis, like MAC channels and like all these MAC medium axis schemes and so on. Okay. One point that I did not kind of go through in this session is this family of what are called lattice processes. Okay. So in lattice, what happens is you would have studied in, I think physics or chemistry, right? We would have studied how atoms in bonds and, this salt is, for example, NaCl has this lattice structure, right? So you can actually model point processes where the points of interest are the lattice sites, okay? And you can, for example, have lattice defects. You cannot have points at certain lattice sites and so on, correct? So that's also another line of inquiry. And there's a lot of things you can do even with Poisson processes, like, for example, Cox process and so on, right? And you can have things like point process on lines, point process on curves and so on. So that's also another very rich line of work. Okay. So with that, I want to kind of close this particular talk. And these are the references. These are some very standard textbooks. Yeah. Okay. This gentleman happens to be my PhD supervisor. Okay. So he's a very good. His books are very good. We happen to have them, and this is also a very good resource. François Bocelli, he's a mathematician. He's also his books are also very good. This is a very nice review article on stochastic geometry. But this is not specifically UAV tuned, but a lot of issues that are shown up here are also relevant to UAVs. So in that sense, it's useful. Okay. So that's basically the thing. If there's any questions, I'll be happy to answer.
Any questions, please? Before we close, there are some more online participants are there, and the Professor Kamesh is also there.
Yes,
Professor Kamesh, can you want to join?
Yeah. In fact, just first of all, it's a wonderful presentation. I believe kind of very useful for, especially for the young researchers over here in the audience. I'm sitting in my room. I'm not at IIT, but I'm just sitting in my guest house. So Sundar, I have one question. What is the motivation for you to? What is the motivation behind this this research? Actually, what are the kind of problems you're trying to address? I'm assuming that you're building the foundation. You build the foundation here.
Sure. Yeah. So thanks for the kind words. First of all, there is quite a bit of work that has already been done in this area for two-dimensional networks. Okay. So there is a very large body of work where people have looked at heterogeneous networks and so on. Okay, from a cellular standpoint. One of the things that we are working on, this is actually a project from Qualcomm, is that for non-terrestrial networks, okay, a lot of these problems are reopened because you will have three-dimensional point processes, okay, which are not really sort of amenable to this, which don't have the same problems, or actually they come up with some interesting other issues that are not there in two dimensions. So Taiba, who is my PhD student, will discuss a couple of them during this demo. Okay. At a more deeper level, I think there's a lot of fertile ground where this point process theory is a model-based approach. If you think about it from a different standpoint, right? You have these point processes where you have this analytical way of looking at it, right? The other side of the story involves a lot of machine learning methods. Okay, right? So one of the things that has sort of recently caught our interest, and we have a small paper on that, is that we can actually start combining tools from machine learning and stochastic geometry to actually say something very concrete about machine learning algorithms themselves. How much can they perform, right? Or what kind of geometries are well suited for machine learning, correct? Network geometries, right? What sort of network architectures are superior, right? And we can actually say something very concrete in terms of, the average time it takes to learn, okay? Or the average data set size you need to meet a certain requirement for a given communication range and so on, right? So a lot of interesting problems come up at this intersection of these two areas. And that's another direction that we are pursuing.
Okay, yeah. Wonderful. Actually, one question is, I work in practical deployments. Most of my work is in addition to some basic theoretical papers, but actually work on practical drone demonstrations and more specifically like drone deliveries and air taxis. These are the things that are going on in Dallas Fort Worth. So the question here is, like you mentioned briefly that okay, we can have some no-fly zones. Some you brought up that some, and then I think I also understood that when you showed like a small area within a bigger area, probably those kind of principles will be useful for drawing some areas where drones will not fly. So you can make this geometry the problem that the ideas that you presented more practical. But one question is, in reality, in the real world, very small areas are will be designated for drones.
Yes.
Think about like let's say air taxis.
Yes.
Or even drone deliveries. They occupy probably they actually are allowed to fly only in designated areas, just like the way vehicles on the roads.
True.
Vehicles, yeah, they won't go everywhere, like
True.
point to point,
True.
but they only. So what do you think? How you can what you call tailor?
Yes.
The ideas that you presented to more practical real world applications.
Yes, that's a very interesting and very relevant point. So, we also have a slide for that also, interestingly, but I will tell you what we will tell. Okay.
Okay. Otherwise, Professor Sundar, thank you very much for the nice presentation. I also enjoyed the presentation, and I have also learned something on the point process and the binary point process. And the demos what you are going to show next, I think it will help us in the participants in understanding the mathematical model, how it can be realized and how it can be demonstrated.
Yes. Thank you. Thank you so much for the opportunity. I'll ask Taiba. Yeah, I'll be there. I'll ask Taiba to start this thing, right? Yeah. Taiba, you can start your video. I will probably briefly pause my video.
Yeah, okay, sir.
So you will close your presentation?
Yes, I will do it right away.
Hello, everybody. I'm Taiba. I'm a PhD student working under the supervision of Dr. Sundar Vanka. I hope my screen is visible and I'm audible enough.
Your video on?
Yeah, my video is on, sir.
No, your camera.
I've joined through two devices, one through the tab and another through a laptop.
Yeah, you can proceed, ma'am, but can you put the camera?
I've joined through two devices. Maybe that is the reason why that is not visible.
Because the video recording, we are unable to capture you.
Okay, I see.
Yeah, that's okay, ma'am.
Okay, sure. So let us start with a brief recap of what was previously presented by Professor Sundar. So the first picture that you see here is a real-time deployment of cellular base stations in central London. Okay. Contrary to what we have studied in the wireless communications course, like how we expected to have this nice hexagonal grids, we see some random deployment, given that there is a lot of uncertainty in where you place the base stations, given the randomness in location, as in sometimes you do not get a place for lease. So all these factors affect and will not let you have a very nice grid kind of pattern when you are about to deploy the base stations. So you can see this particular pattern as one realization of a point process, for example. Now, the reason why we need this point process models or all the math behind this is that suppose that there was a user, suppose that we are looking at this region. Suppose that we are looking at this region and there was a user, there is a user somewhere here. Okay. Now suppose we want to study the performance experienced by this user given this base station deployment, given these red dots are the base stations. Suppose that we are interested in finding the performance experienced by the user in this particular area. Now, if we assume that there is some particular pattern or there is some deterministic pattern, and if we study the performance for that particular pattern, that is not a efficient way of saying that for so and so pattern we are seeing so and so performance. That would be very hardcore way of saying that. Instead of saying that, if we say something more solid, as in for any random spatial pattern in this grid, we achieve this average performance at the user. That is a more stronger statement that we can give. And such kind of analysis is allowed if we model the base station locations using some mathematical models that we have discussed, that we have seen in the previous version of the course. We have seen something called binomial point process. We have seen something called Poisson point process, right? So all these models are used to specify the base station point pattern, and we can study the performance at any user or maybe a UAV too. Now, given this background, so these initial slides are to give a brief idea on what a spatial realization is and what a point process is. But I'll try to quickly glance over this because this was already very briefly, very in detail covered in the first half of this course. So if you take a simple die experiment where you roll a die, the outcome that we usually, till now at least, we expect is a number from 1 to 6, right? But if we map the number 1 to some pattern in space, that would be something like this. Otherwise, if we map number 3 to some pattern in space, it would look like this. Similarly, if a guy here has rolled a die and the outcome that was seen was 5. The pattern that you see in space is 5 points in the space at these specified locations here. Oh, I see. Just a second. I've turned it off, but okay, let me present through my laptop only. I'll log out of the tab. Is my screen visible, sir?
Keep it. Yes. Yes.
Yeah. Yeah. So if you recall one of the slides from Professor Vanka's presentation, there was an analogy between the random variable and the point process phi, wherein you had random variable x that maps omega1 to some value, say x1, and some another outcome omega2 that maps to another random variable x2. Similarly, here the outcome phi that you see, phi is one of the, you can see it as some omega1. It maps to a pattern called 5 dots on the 2D grid, right? So this point process is what we call as a die point process. This is only just to form a foundation on what specific terms are. For example, this particular thing is called a pattern or a realization. And the set of realizations that we see are 0 for omega 1 equal to 1, and for outcome as 2, you see points at 1 comma 1 minus 1 comma 1 and 1 comma minus 1. So this way, these are all the set of realizations that you see. Now, here in this experiment, at least you know what the random experiment is. But suppose you don't know what a random experiment is. You say some random experiment, some unknown random experiment has resulted in a pattern or a realization. Then how would the then what are different kinds of models we have to model such patterns is what we are going to see in today's demo. And here are a few few workout examples that you can try. You can take a screenshot of this and try later. But in the interest of time, I'm right now skipping this slide. Just to give a hint, the probability that a point is present at 0, 0 corresponds to all those events where there is a dot at 0. For example, you see at origin, you see a point at origin when the outcome is 5, or when the outcome is 1, or when the outcome is 3, right? So the probability of all these 3 occurring is what you get as the answer. Similarly, you have something called conditioning event, where you condition on a point at origin and find the probability that there is a point at minus 1 comma 1. Now, if you look in the previous example, the number of realizations that we see, for example, from 1 to 6, you have 6 realizations of the point process. But it is not necessary that there are finite number of realizations, right? For example, if you are looking at a continuous space, say R2, you can have points anywhere on R2. So this results in having some infinite number of realizations of a point process. So that is one takeaway. Now, unlike the previous example, suppose that we don't know what the random experiment was, but we saw some pattern or some realization of points on a line or a plane. Let's see how we can, let's see what are different kinds of models. Okay, and we'll start with something called, we have exactly n points in a pattern, which corresponds to the binomial point process that we have seen in the first part of the course. We start with assuming that n is deterministic, as in you fix the value of n, it is not drawn from any random variable. It's not a random variable, it's a deterministic quantity. And different ways of placing the n points gives you different kinds of models. For example, if you see here, we have modeled, we have drawn n points where n is 20 in this example from a Gaussian PDF. Okay, so this is one realization of a point pattern on line. You may ask me, where do you see this? Imagine an example where you have a straight line or maybe a highway or a beach side where there are some stalls or there are some shops or where the population is more concentrated. Okay, you might want to install drones in those regions to serve the users that are present, who are present on the ground. So you would want to install a UAVs in air where there are more number of UAVs concentrated around this some mean where there are more population, and less number of UAVs in air towards the edges. So this is one example where you can see the UAVs are modeled on a line in air, but the underlying model is a Gaussian model. Similarly, if you look at another way of modeling such thing is uniform, drawing the points from a uniform PDF. If you see from this is again one realization of point pattern for n equal to 20. We are drawing n points at random, but uniformly and IID at random. Okay, so the example where you see this is suppose you have a highway and you are trying to you want to install drones to sense some kind of activity on the highway. You might want to have drones evenly spaced across the road, right? So the model that you can choose for such application is you want uniform deployment of drones along a line or along the highway. So this is one real life example. And still now we have seen it in 1D, right? We have seen point realizations in 1D. When it comes to 2D, you can start with 2D Gaussian. For example, there is a there is a area which got affected with some fire, and you want to install drones to either capture the present status of the place, or you might want to ask the drones to spray water, like how the example that is shown here. It is trying to suppose they are firefighter drones. Okay. You might want the drones to concentrate in one certain region and not to have too many in the surroundings. So you can see this, it can be modeled using a 2D Gaussian PDF, which is having some positive correlation coefficient. Similarly, if you want the drones to be evenly distributed in a circle on a disk, then you can have points drawn. You can have endpoints drawn from a 2D Gaussian PDF. So these are different ways of modeling a spatial point pattern. Now, I'm not exactly going through the MATLAB codes in the interest of time, but I can show you one MATLAB code that demonstrates the uniform PDF on a single line, because that will help you do the exercise that is in the upcoming slide. Yeah.
I'm not able to see it. Yeah, you can just walk them through. Yeah, please.
Yeah. So this code. Okay, sure. Okay, sir. Yeah. So this particular code will randomly pick endpoints from a uniform PDF, from a one-dimensional uniform PDF. The number of points that we chose here are 20. You can always change this value, and we are drawing endpoints at random on a line from -4 to 4. Okay, and the way you pick endpoints at random is you start with the uniform. You start with the random generator. RAND, it does the job of picking n values, because 1 by n is so even before that, rand of 1 comma n, the job of sorry, sir. Okay. Maybe I'll try to.
Can you go to view? Yeah, view. There'll be a zoom in. Can you say there's a zoom in there? Just press that a couple of times. This is super. This is good. Is this good?
Okay. That's good. Okay. Is this good now? Okay.
Yes. Yeah.
Okay, so thank you. Yeah. So let me repeat that in case anyone among you have missed it. So we start with a value n as 20. So we are trying to pick 20 points at random from a uniform PDF, and we define the line. We are trying to pick the points on a line whose length is 8. That is, it is from -4 to 4. Yeah. So the way we generate these endpoints at random from a uniform PDF is given by this line 11. I'll now explain how what exactly this does. Okay, the rand function, in general the rand function, it tries to pick 1 by n size of elements from a uniform distribution between 0, 1. Okay, so the job of rand of 1, n is to pick randomly distributed point from a uniform PDF 0, 1. Since we want the distribution from -4 to 4, we will try to scale it to 8, as in Okay, then just fine. Yeah. So the way the multiplication factor b minus c ensures that correct. Yeah, that's it. So yeah, so once we when we run this, So what you see here is a realization of points, 20 points drawn from a uniform PDF. The next slide in the presentation, it asks you to do this in 2D. As in, till now we have seen how to draw points from a 1D from a one-dimensional line, right? So this asks you to do it in a two-dimensional line. You can take a screenshot of this and try later, but it is same as what we have seen in 1D, except that you have to draw from a two-dimensional plane. As in, x should be drawn from -5 to 5, some 20 points from -5 to 5, and 20 points from on the y-axis. So that's how you get the IID uniform distributed points drawn at random.
I want to add one small point here. Changing it to rectangle is easy, but I think if participants want to understand how these forms are also deployed, maybe something like a disk is also very useful.
Yeah.
So the A, they can choose whatever they want. It can be in 2-dimension or 3-dimension, right?
Correct.
So they can do the same thing for 2 and 3 dimensions to model a swarm.
Right. So the way you do that, the way you do it is you will have this theta, which captures the angle at which the point is located, that is uniformly distributed, and you will have the radius. Suppose if it is a 2D disk, you will have a radius proportional to square root of uniform. That's a basic concept that is there in the probability theory. You can go through that and try to generate points using this concept. Okay. So till now we have seen what has happened in 1D and 2D. The 3D case can be seen as just a stack of 2D disks. For example, if you imagine a 3D, if you imagine drones present in air, they can be realized using some n number of disks, wherein in each disk you generate some few points according to uniform PDF. So this is what we call as uniform binomial point process in 3D. Okay. It's just like stitching the 2D disks to get a 3D cylinder or a 3D pattern in space. So in the literature, there are a lot of works who try to model UAV locations using this binomial point process in a cylinder, or who try to model the swarm locations of who try to model the swarm of UAVs using the models that we have discussed before. You can go through this papers and see how they have used these models to generate some insights. So in the upcoming slides, we'll see what if n is random. For example, in the previous slide, we fixed n to be some deterministic value, right? Now, what if n is some random variable? It can drawn from any distribution, for example, Poisson or uniform or geometric or binomial. Now, given that you have chosen a random n value, you can ask to place those n points uniformly and IID at random in the given tile. So this generates one kind of process. The reason why I am starting with this is we'll generalize this to something called something like having n drawn from Poisson PMF from in all the tiles. So if you recall the slides presented by Professor Sundar, you can see you can see that or else. Okay, let me not go there, but the main takeaway that I want you to take here is in each tile you have a different intensity of points. So all these different intensities in a given area would result in a point process, something called inhomogeneous point process. The reason why it is called inhomogeneous is if you look at the area, this area from 4 to 8 and 0 to 4, although both the tiles have equal areas, the intensity in each of these tiles is different, causing it to not have a homogeneous process. If we make sure that the average number of points in each tile is proportional to the area, that's when we end up having a homogeneous point process. This was already discussed in the previous in the first part of the course, so I'm not going very much in detail. You can go through the MATLAB codes which demonstrate how dividing each rectangular tile into further smaller grids would end up having again a separate PPP of the same intensity.
So I have one point that I want to mention here, to kind of chime in with what Taiba said. If you see on slide number 14, that is what she's showing now. Okay, so you see this is like on the left, there are two plots that you see. On the left, there is basically a point process where you have lambda, which is 10, and one of them is 50. Is it everything is 10?
Yeah, everything is 10, sir.
Okay, so that labeling, okay. So what you can see here is that you can kind of intuitively at least get a feel that you are getting a different collection of random points as you move from one tile to the other, correct? They look quote unquote similar in the sense that they look similarly random. There's no specific pattern in each of them, right? So, and if you see the same thing, it is being played out when you look at the 16 subdivided grids, right? So this actually goes back to this idea about ergodicity that we discussed, right? So what is happening is, because this is an ergodic process, okay, your ability to actually find certain averages, okay, and find the average over all the tiles, okay, is sort of bolstered because the process itself seems to be kind of creating quote unquote a new version of itself every time, right? So that you don't need to have separate realizations to get your average. Okay, so that's one point that is kind of showing up here. Right? Yeah, please.
Yeah.
Need to see carefully both the pictures,
Yes.
the points.
Yes.
The points are stationary, and the divisions have been made 4 to 16.
Yes. Yes.
Is it right, sir?
Yes, correct.
Both the pictures have same locations
Yes,
of
yes,
the
they're the
points.
same. They're the same. You're right.
Yeah, yeah. Okay.
Good observation.
Oh,
Yeah.
thank you, sir.
Yes, yes, yes. The only thing is, I think what she's trying to show here is that she was trying to show homogeneity. I was kind of adding another context to it, saying that, you know, you can even notice, you can get a feel for why it is ergodic,
Yeah.
right? You're kind of
that's true,
seeing different copies of that small tile, right? Different versions of that small tile show up in different of these, all these smaller tiles.
Yes,
right?
sir.
So the first tile, second tile. So what is happening is you can take the average of all of them without waiting for another realization of the PPP.
Right, sir. Ensembled average if you have to take.
Yes. So that just like, for example, if you take a stochastic process in time, you can just average out.
So these have been simulated for how many runs, sir? 10,000 or more than that, sir?
This is a single realization.
Single rail, but
Yes.
if I run it again, it will come different.
Yeah.
Yes, it will become different.
So,
Exactly.
but you have not tried it by ensembling, averaging over 10,000 time or something.
So if I ensemble average, no,
Yeah.
I cannot show you something like this.
Okay. Then
Right?
it will be
Because-
stationary, sir, almost.
No, if I do any averaging like that, I'll get a single number out.
Only single number we get. Yeah, that's.
I have to say something about the average, right? I think the main motivation that she is done, what we're doing here is that we're trying to show homogeneity. So if you see the first thing, different tiles, the point process looks very similar.
Okay.
There's not something particularly different between the two.
Yeah,
Right.
there is no particular difference.
There is no
Right.
pattern present.
Okay.
Right.
Thank
And
you.
another thing is, it is almost as if, you know, somebody took, you know, one tile of the point process,
Yeah.
and the next tile is basically some
Guesswork
other
can be
version.
done. Based on that,
Ah.
we can do the guesswork. Okay.
So that homogeneity and ergodicity are coming in like this, very, very naturally in this case, is
Yes,
what
sir,
I'm
that is clear from this. Okay, sir. Thank
Yes,
you.
yes, yeah.
So, yeah, this is again when you divide it into 64 subgrids, you again see the same intensity in each of the grids, is showing that the process is homogeneous. And this definition has already been introduced in the previous slides, so I'm skipping it for now. And if you see some real life examples, suppose you have a coffee cup and you're trying to sprinkling the coffee powder at some height, and what you see is a uniformly distributed powder on the cup. For example, if you look at the cake example also, if you take some randomly picked number of choco chips, if you sprinkle it uniformly at random, what you get is a Poisson point process. So both these examples can be seen as, you know, some real life examples for PPPs. Now that we have seen how it is in 2D, if we want to model UAVs in 3D, for example, in the binomial point process case, we have seen that we have modeled each layer as some disk, and from on each disk we have picked points at uniformly at random. Similarly, if you want a 3D PPP in space, what you can do is you can divide the space into some planes or even disks here, and you can fill each plane or each disk with Poisson distributed number of points, which are picked uniformly at random. So this is just a demonstrate the reason why the intensity goes down as we go high is very much tied in with the real life modeling of UAVs. For example, if you want to deploy UAVs in 3D, you would not want to have UAVs too high because you want to avoid the large scale path loss efficiently. If the UAV is placed somewhere here, it is very much possible that it will experience very high large scale path loss, resulting in a decreased performance. So you can always model the intensity of the point process such that as the height goes up, the number of points present on the higher heights are lesser. So this is one way of modeling a 3D PPP. You can always have equal intensity on all the planes, but that is one model. That is one way of modeling, and this is one way of modeling it. Many different kinds of models are in use in the literature. Few among them we have mentioned here. One is a Poisson cluster process, and the other is a Poisson line process. We'll start with what a Poisson cluster process is. Suppose that there are a collection of base stations who are trying to serve the UAVs present in air, and even before that, let me formally introduce you what a Poisson cluster process is. A Poisson cluster process is something where you have the parent UAVs, which are present which are blue in color, which are marked blue in color, are distributed according to a PPP, and you have child UAVs around each parent UAV, distributed uniformly or in a Gaussian or using a Gaussian model. Any model, you can choose any model for that matter. Depending on what model you choose for the child UAVs, you will get a different kind of cluster process. So in this particular example, we have chosen them to be uniformly distributed in the 3D space. So this is what we call as Poisson cluster process. So using this model, what people have done in the literature is they would study what is the performance seen at a UAV, assuming that all the UAVs are being served by this base station. So this is one mathematical model people use. And one thing I would want to highlight here is it is not necessary that there is always a parent UAV in each cluster. You can as well note it as some reference point around which the child UAVs are distributed in a disk, in a cylinder, or in a sphere, or in any rectangular grid. So it is not necessary that you have a parent UAV in each cluster. And also, in real life, when you want to model this close to the real life examples, you would want to induce some repulsion between the clusters, because you do not. It is not efficient to have two clusters at the same point doing the same job, right? So we would want to introduce some kind of repulsion between the clusters so that no two clusters overlap. So this is one kind of model. The other model is the Poisson line process. So if I don't know how many of you have seen this, but there is a recent ad by Swiggy Instamart wherein the drones try to deliver the products or the okay. So they try to deliver the products or the goods to the specified location. So it's a similar example wherein there is a warehouse which is trying to deliver goods to some areas in the city, and the UAVs are following some specified path or along in the 3D space. For example, you can see you can view them as aerial highways, as in you have some predefined paths over which the UAVs should travel, and all these UAVs are being served by the base stations on ground. When I say they are being served, they are being controlled. They will communicate with the base station. Maybe they will send their coordinates, or maybe they will tell their status, or maybe they will share their speed. Okay, all these are kinds of data that will be exchanged between these base stations and the UAVs. So this communication network, given this communication network, people would want to study the performance of the installed UAV. So this can be modeled using a process called Poisson line process, wherein we pick Poisson number of lines. Here I have aligned them horizontally and vertically to essentially map it to the example that I'm showing here. But in general, it is not necessary that they are only horizontal and vertical. They can be randomly oriented. Okay, and given each line, you randomly sample UAVs from a Poisson process. That's how we end up having a Poisson line process. I'll briefly walk you through the code for both the Poisson cluster process and the line process. So I'm talking about. So I'm talking about this process.
Again, can you make the MATLAB code bigger when you're presenting?
Yeah, I'll do that. So.
Yeah.
So we are now seeing how to obtain this model in MATLAB. Is this sufficient? Hello, sir.
It is okay with me. Is it okay, Professor Saipat?
Hello.
Okay, great, perfect.
Okay.
Yeah.
Yeah. So on screen so that you can show it better. No, it's not allowing me to do that. Okay. So the lambda base station here corresponds to the base station point process intensity, and lambda UAV corresponds to the parent process intensity. All the UAVs in the blue are the parent UAVs. So the intensity is given by lambda UAV. And the child UAVs have an intensity of 5, which means they are on an average 5 number of UAVs per parent UAV. So we can determine the cluster radius, cluster height, parent height. All these are the parameters that we can tune.
So one small correction. Lambda UAV is 5. Lambda child is 5. Means that the mean number of children per UAV is 5 multiplied by the volume of that.
Volume of that.
So that's pi times 2 square times 1.
Right.
Yeah. Yes. So one more point worth mentioning. I don't know whether you already mentioned it.
Okay.
In this case, the blue dots, which is the parent sort of points, may or may not actually have a UAV there.
Yeah, I have mentioned that.
You mentioned that. Okay. Yeah, I think that should be. It's a very important, subtle point, right?
Yeah. So it is not necessary that we always have a parent UAV. It can be some reference point around which the child UAVs are distributed.
Yes.
Yeah. So the way we generate PPP for ground-based, so this is a general way to generate PPP. We first pick n. We saw that n is random, right? So n is random, whose mean is given by lambda times the area in which we are trying to generate. So area is given by 20. So it's a square area. So area size square gives you the Lebesgue measure of that plane that we are looking at, and lambda base station is the intensity. So given this mean, you will first generate the number of base stations, which is a Poisson distributed random variable. Once you have that, we generate that many number of points uniformly at random. Okay, and since the base stations are assumed at 0 height, we have along the z-axis we have zeros. Similarly, we follow the same code to generate the parent UAVs. And once you have parent UAVs, you can generate child UAVs using any model that you want. For example, here we have generated them uniformly at random. You can as well generate the child UAVs according to some 3D Gaussian process, meaning you can have you can have child UAVs closer at the center and very sparse along the edges of the cylinder. Okay, that's one way of modeling. We will call that Martin core process. We'll not get into that, but I'm just trying to tell you that there are different kinds of cluster processes. Okay, here again, given each parent for I equal to 1 to number of parents, we are trying to generate the child UAVs according to Poisson random variable. So here, if you see, we are trying to place the UAVs on a disk. That is where you see that theta is uniformly randomly distributed, but R is square root of uniform multiplied by the radius that we have. So this is what I was mentioning when I said the points are uniformly distributed on a disk or a sphere of a given radius. And the rest is all just plotting the obtained points using the scatter plots. So this can be understood. This is how you generate a Poisson cluster process. When you see a Poisson line process is something that I mentioned here. Yeah. So this is what I'm referring to right now, a Poisson line process.
You need to zoom it, please. I can't read it.
No, I've already presented it, sir.
Is it? Okay, sorry. Maybe my eyesight is bad, yeah.
No, this I have already presented. I did not most to them. So I'm
okay, sounds good. Okay.
Yeah. So this is we'll see how this was generated now. Okay.
So just to give some context here. Hello?
As I said, a Poisson line process is something where you generate first Poisson.
Your voice is cut out. I don't know if it's an issue with my network or did everyone see this issue? Oh, I see. No. I think the problem is I could not hear Taiba's voice very well. It cut out. I was wondering whether it's just me or...
Is it better now, sir?
Yes, it's better now. Yeah.
Yeah, I'm meant to present it, sir.
Yeah, please carry on.
Yeah, so you were mentioning something. You wanted to add something to this?
Yeah. As Professor Kamesh said, see, these line processes are a way to impose structure on the UAV traffic. Correct. So instead of saying that UAVs can travel wherever they want, whenever they want, we impose certain regions where they can exist. And conversely, if someone uses things like the whole process, you can also impose regions where they cannot exist.
Correct.
Right. So that's something that we're using this Poisson framework to define point process on objects which are not just a plane or a cylinder or a Borel set. We're trying to convert into other things.
Right.
Just to give that context. Yeah.
So we'll see how this was generated. So as I mentioned previously, Poisson line process is something where you have Poisson number of lines oriented in the 3D space. And once you have have a line, you have to generate the Poisson number of points on the each line. So here lambda L corresponds to the intensity of the lines, and lambda P corresponds to the intensity of UAV per line. So we have initiated this area size with 3, and we are assuming the height range is from 2 to 8. You can always here you are trying to generate a Poisson random variable, which is a Poisson number of lines, and once you have that, here these lines of code usually what they are trying to do is they are generating either a horizontal line or a vertical line with a 50% probability. Since
Taiba, can you hear me? I think professor is trying. Yeah, the professor is trying to say something.
Yeah. No, it has been completed. So I have shared the slides with you, right? They're already. Yeah, they're already there in it. Yeah.
Yeah, you can share the
Sure.
source code can be shared. Yeah. Which one?
No,
which
sure.
Which ones are we referring to? Which ones are we referring to?
No, sir. Share.
Yeah. These are actually pretty standard codes. Yeah. So you can take them. I think so if the participants want to do it, then that will be even better. Yeah. That will also actually, Taiba, that will also help you sort of maybe if they're able to run it by themselves, they can review the code, because all these comments are very standard comments. There's nothing special, right? So my suggestion is we can.
No, these are just.
Yeah.
The demo.
Actually, I don't know whether it's an issue with my network or network on that side. Okay, because you're able to hear me when I talk, no? Okay.
Shall I turn off my videos?
Yeah, maybe that's the issue.
Okay. Yeah, that's one.
There are few interruptions while you are presenting. The screen is visible, but while presenting, there is an interruption.
No, I think the audio was getting cut out very often. I think that was the issue.
Yes.
I for a good part, I did not even follow what was happening because it was too much of,
Okay. Yeah. Am I audible now, sir?
Yeah. Now I think your voice is clear, but slides we have to see.
Yeah. I'm able to present them.
Now it is good, ma'am.
Okay, thank you, sir. So shall I continue?
Yeah, continue, ma'am.
Okay. So till now we have seen different ways to model UAV point process. Different ways, as in the Poisson line process, or the cluster process, or the PPPs or the BPPs. Now we'll see where exactly are these used to study the performance of a network. So these are actually a part of our work, which we have. These are the accepted works at Globecom and ICASP. I'll present them in a while. But before that, we'll briefly see different kinds of applications and different kinds of implications that we have in a UAV network. So yeah. So if you look at the figure on the left, here a typical user is receiving service from both the ground base stations and the aerial base stations. Aerial base stations refer to the UAVs. So you can view this as a use case where we are trying to improve the performance of the seen at the typical user, given that there are some buildings on the ground, because of which these paths from the base stations are being blocked. In that case, you can ask for UAVs to provide the service to the user and improve the performance at the typical user. So that can be seen as one application where UAVs are used as aerial base stations. That is, having to have a line of sight link between the base station and the typical user, which is not usually seen on the ground base station to the user link. But having said that, it is not always true that UAV to the user link is line of sight. It can be non-line of sight too. I'll come to that in a while. The reason why the link between the UAV and the user can be non-line of sight is that there are some limitations given by FAA. There are some limits given by FAA. That is, you cannot deploy UAVs beyond certain height, say 400 feet. It is around some 120 or 130 meters. So given that constraint of UAV height deployment, you can see that the UAV links between the links between the UAVs and the users on the ground are also blocked by the buildings, any tall buildings in the urban areas for that matter. So those links are also susceptible to blockages, especially when we are using millimeter waves for the communication. So if you use millimeter waves, they are more susceptible to absorption, right? So the link is instantaneously non-line of sight. But to model this feature also, as in to model whether the link is line of sight or non-line of sight, ITU has proposed a model wherein it's a probabilistic model which tells you, based on the distance between the user height and the transmitter height, as a function of some parameters, it will give with some probability this link is line of sight, or with some probability this link is non-line of sight. So PL of delta R is that probability with which the link can be in line of sight. It is a function of many parameters like height of the transmitter, height of the difference between the heights, or lambda A and lambda B corresponds to the blockage density. Blockages as in the building densities, and lambda A corresponds to what is the ratio of building area to the total area. So it's a function of all these parameters. Once you have that probability, you can view it as some Bernoulli random variable with probability P. So suppose there is a link, UAV, suppose the link is between the UAV and the user on ground. If suppose that given all these parameters, you have a probability, say 0.5. So with 50% probability, the link is in line of sight, and with 50% probability, it is in non-line of sight. You can view it as a Bernoulli random variable with probability P. And this is a little mathematically more involved model, which leads to some interactability when you try to use this in the math. So one simple model people have been using is this ball model, wherein
Saiba, I think Professor Sai Prakash has a question.
Yeah,
Okay.
ma'am. Epsilon you have used, it is the environment or what, madam?
Which one, sir?
Epsilon?
Epsilon, it is the average building height. I'm sorry,
Average
I forgot to
building height.
mention
Okay,
it here.
okay.
Yeah,
Right.
epsilon is the average building height in a given environment. Suppose, so there are values given for this epsilon,
That is
delta
okay.
R, lambda A and lambda B for
Okay.
each environment. If it is suburban, there are some set of values that are
No,
predefined.
there is a square root 2 epsilon delta, right?
Right.
The epsilon is
Epsilon is the average building height.
Okay.
So if we look here,
Yeah.
I need to.
Yeah, that is really constant.
Yeah, it's a constant given a particular environment.
Yeah, right.
If it is a rural area, epsilon will be very less. If it is an urban area, it will be high. That's how it is modeled.
Instead of that, why can't we use the Nakagami channel or what? When there is building height, the epsilon will go beyond 1 and above 1.
No. Oh, okay.
So I think no, I think I'll let you answer. I have a slightly different point. I think I'll let you answer the professor's question first.
Okay. So I think the building density, the building height can be modeled with any random variable given the environment. That's what I think so.
Thank you, ma'am. That is.
No, I think Professor Sai Prakash Garu. So here is the thing, right? At least I want to give a slightly different my understanding of this equation. Correct? This whenever at least I see a probability and a sum of some more terms, I tend to look at them as probabilities again. So probability of A multiplied probability of B and so on.
Yeah.
So basically what they are saying is something is line of sight only when everything in the path is line of sight. Even if there is one blockage, it cannot be line of sight.
Yeah, that is true, sir. That's why I'm saying that if it is Nakagami cell, we can tune the parameter either this way or that way.
Exactly. So what happens is this Nakagami parameter that you're talking about should be a function of the density of blockages, which is the density of buildings basically. Okay. And in some sense, a blockage to total area is something like the width of the buildings.
Yeah, that means that we should have a perfect channel feedback which tells what the value of
No. There's no channel feedback necessary.
But
because
height,
as you know,
how we'll know that height and all?
No, height is known, sir. Height is known because the height comes from
the receiver. Okay.
So as you know, these UAVs have a IMU.
Okay, I thought at the
so they have IMU, no?
No, I thought it is at the drone. Okay, sir, that is fine.
So what I'm saying is this Nakagami parameter that you're talking about is a function of two things basically: the distance and the height. Okay, and the density of things that comes in between. So if the probability of line of sight is a probability that everything in between the height is below a certain point.
Yeah, that is. Okay. It tells us whether it is a dense urban or rural.
Exactly. So what happens is basically if all these terms 1 minus expo of this, those are all very small. That means expo of this is close to 1. Okay.
Right.
That means let's say the numerator, for example, is close to 0. Then that means there's basically very little chance that it will be line of sight. Okay.
But as the range goes to 60 gigahertz, what happens, sir?
Yes. So that's an interesting point. All these things assume that we are in the not in the. I don't believe that this model is accurate enough for millimeter wave.
The object height is more than the lambda, then it will not
yes.
get totally...
And the other problem with 60 gigahertz is that unlike, let's say, sub-6 gigahertz spectrum, 60 gigahertz, there is no diffraction.
Yeah, no diffraction.
So therefore, it cannot even penetrate. I mean, there's a joke that if you have a millimeter wave connection between your mobile phone and TV and you're watching a movie, even if your dog or your child comes in the middle, okay, the movie streaming is stopped.
That's what's happening right now, sir. When a call comes in, we are running out instead of staying inside the house.
So that is why the millimeter wave propagation is actually very sensitive. And in fact, the second part is also there. The people are talking about terahertz.
Yeah.
So terahertz, it will have even more of an issue than
that's why we are limiting the size only to the room, only at the access point only.
Right. So this is a chance, I think, on a slightly different note, the future way in which we'll probably communicate will mean using different bands for different distances. So if you want, let us say within a room, maybe you'll use terahertz.
That's what the new radio says. But we don't know how it goes.
Yes. So that's probably how they'll do it. Only thing with these cases is only time will tell whether there are use cases that use it. That's a problem. Yeah.
Because back end they are pushing everything into fiber, so they're assuming that front end it can go.
Yes.
Right,
yes.
sir. Thank you, sir. Thank you.
Yes. Yes. Sure. Yeah.
Yeah. So one more point that I want to add here is this model assumes that independent of whether a user is blocked or not, the user behind it, suppose that there are two users at this point and at this point. It does not assume that all the users beyond this point are all blocked, because it independently chooses whether a user is blocked or not, irrespective of whether a building is present in that region or not. So that is one drawback that we thought that is in this model. To mitigate that, people have used a different model which is more mathematically tractable, which is this ball model, wherein people say, see, if at all the links are within certain radius, say capital R here, all those links will be in line of sight, and everything after that will have non-line of sight. So all the users after this disk will experience non-line of sight with the UAV, and all the users within this disk will experience line of sight. So this is a fairly simple model to implement, in a mathematical sense, and to gain more insights. So given this, we'll start with the motivation to the work that we have done. If we look at the existing architecture, suppose LAN connected computers or the cellular network, we all know what protocols these are designed. For example, if you look at a cellular network, there are some handoff mechanisms when the user moves from one cell to another cell. They're all predefined. But when it comes to UAVs, if at all UAVs are viewed as some users in air, there are no design considerations which will tell you how should the ground network be designed such that we can best serve these UAVs. So this is a different perspective compared to what has already been done in this area. So in the existing literature, people have viewed UAVs as some elements which are providing service to the users on the ground. For example, if you look at this example, UAVs are acting as additional infrastructure in the air who are trying to improve the performance of the typical user. But we ask a slightly different question. What if UAVs themselves need service? What if they needs to be controlled? And what are some design considerations that need to be kept in mind? One very first question one may ask is, how should the ground base station should be designed such that we see good performance in a UAV network? Two ways in which this differs is the kind of traffic that we see. For example, if you look at the ground users, the kind of traffic that you see is basically either the text images or the video images or some kind of not mission critical data. So it is not the data that you exchange is not critical. It's not time sensitive. You can wait for a second or so to receive the data. But when you look at UAVs as users, that is not the case. If at all UAV does not receive some data within some fraction amount, within some time, the mission may fail. Maybe the UAVs were on a mission where they want to, identify some object on the ground, and they have some time limit within which they should do that. If the UAVs cannot receive that data for whatsoever reason, the mission would fail. So these are the kinds of challenges that one would face if UAVs are used as users. In our work, we'll see how a network is designed and how different parameters in the system would affect the system performance. So our first work is on infrastructure design for large UAV networks. Here, we have assumed that the ground base stations follow a Poisson point process, and the UAVs also form a Poisson point process. They are present at some height h, and we assume that everything is static here. Even the UAVs are just hovering in air, they are not moving. And there are two kinds of data that are being communicated. One from the ground base station to the air, to the UAV, that is ground to air link. the kind of traffic is what we call as C2 traffic. C2 traffic is a command and control traffic, which will give command data to the UAVs. Like for example, the base station may ask the UAV to move to the left, to move to the right, or any data that is mission critical. So when I say that data is mission critical, it is usually latency sensitive, as in you should be able to communicate that data within certain slots. Otherwise, you would see a mission failure. Similarly, on the air to ground link, that is from the UAV to the base station, there is this payload traffic, which is throughput concerned, because some kind of data that UAVs transmit are the images or the videos that it has captured. For example, if you see the image here, the UAVs tried capturing the fire accident, or else the UAV here tried capturing the landslide here. It is trying to send the status to some nearby station, maybe a police station or a fire station. So this is a payload. This is what we call as payload traffic. So you want to send more amount of data, right? That's why we call it a throughput concerned data. One thing that I want to highlight here is all this communication is being happened in the presence of interference. If you see carefully, the data received by the UAV, by this UAV, is the signals received at this UAV are being interfered by these red dotted line signals. So assuming that these both are all the base stations are using that same channel, we see interference at this UAV. We'll see how, in the presence of interference, this latency sensitive traffic and the throughput concerned traffic would get affected, and how both these parameters, the delay and the throughput, are a function of this base station density and the UAV density. So this is what I was mentioning. And one more thing I want to add here is the A2G traffic can also be C2 traffic, as in the UAV might be trying to communicate its own coordinates to the base station, saying, "Hey, I'm here, so send me some help." So that might be a kind of latency sensitive data that it wants to transmit to the base station. So the air to ground data can be a combination of payload and C2 traffic, whereas ground to air would be purely C2. So these are some specifications given by 3GPP. If you see, the C2 traffic has a latency constraint of 50 milliseconds, as in within 50 milliseconds, one should be able to communicate the data to the UAV. And payload traffic has a data rate of 50 Mbps, so it should be able to transmit as much big file as possible. But if you see the data rate of the C2 traffic, it is very limited. Reason being, the packets that are transmitted on ground to air are usually of smaller size. They are very small packets which do not need very high data rates. Okay? So given this background, I'll now explain the metric delay that we have studied in this paper. Okay, so sir, I'm still audible, right? Hello?
Yes, you're audible. You're audible.
Yeah.
Go ahead.
Okay. So this is one of the metrics that we have studied in this paper. We call it the mean packet reception delay. If you recall the concepts, and even before that, and even before that, here we assume that each UAV communicates with its nearest base station, as in it receives a C2 traffic from the nearest or the strongest base station. Okay, so that is the reason why I have mentioned it as nearest base station here. So in time slot number 1, suppose the base station is the associated base station is trying to send a C2 packet to the UAV. Due to the reasons that were mentioned in the first slide of this talk, that is the fading or the shadowing, it is possible that the UAV may not decode the packet correctly. So it may fail to decode the packet, and it will send the negative acknowledgement in that case. Then the base station associated with this UAV will try to resend the packet in the next slot. So again, given the randomness in the environment, given the channel conditions, the packet may not be successfully received at the UAV. It will again send a negative acknowledgement. Then the nearest base station would again resend the data. So this time, maybe everything was good, the channel was good, and it got to successfully receive the data. So these number of slots, these 3 slots are what we call as reception delay. Okay, we call it the delay in receiving the packet successfully. That's how it is called, the reception delay. Now you might ask, what is that one metric based on which the successful packet reception, or you may ask, what is that one event based on which packet reception or packet failure is decided? That is the signal to interference ratio being greater than some threshold theta. If at all in the first slot, if the UAV sees that the signal to interference ratio is greater than theta, it would declare that it has successfully received the packet. Else, it would say, I did not receive the packet, so it sends a negative acknowledgement. So if you see the event here, this would have been S by I less than theta. That is why it couldn't decode the packet. In the second slot also, it would have been S by I less than theta. That's the reason UAV could not decode the packet. In the third slot, it was able to decode the packet successfully, which means S by I here was greater than theta. So if you try to recall your concepts from probability theory, it is something like, you see a success after some n failures, right? You saw a failure here, you saw a failure here, and this is the first time you saw the success. So this corresponds to geometric random variable. If you recall the concepts from your basic probability theory, this is the first time you saw the success. I mean, this is the first time you saw successful packet reception. So this random variable, the reception delay, is a geometric random variable. What we are studying here is a mean of that reception delay. When I say mean of reception delay, there are different sources of randomness, right? If you recall from today's course only, in the second or the third slide, we were discussing what should be the expectation upon. It should be on the fading gains, because there is the source of randomness comes from the G factor that was present in the path loss, or even the distances, because if you remember, there was a text in the red, can D be random? Even D can be random. That is one source of randomness. All these randomness accounts to having a randomness. All these sources of randomness will tell you whether the packet will all these sources of randomness will not let you decide on your own whether the packet is successfully received or not. Okay, so the main metric that we are going to calculate here is the mean delay. But if you recall the ergodicity property from the first part of the course, that's what we will be using in the current work. The actual metric that we are interested in is a spatially average delay, as in, suppose that each UAV has a nearest base station associated to it, and each UAV receives some data packets from its ground base station, and on each link there might be some amount of delay. Say the delay on this link is some 10 slots, so the delay on this link is some 2 slots, 5, 6, 7, 8, so on. Okay, the average amount of delay is what we are interested in. So it is like sum of the delays on each links by total number of links is what we are interested in. Okay, but evaluating this spatially average delay is same as finding the ensemble average delay from the ergodicity of the point process. So we will use that property to find the mean delay, and the other property that we use here is the stationarity of the PPP. As in, we will say that the UAV of interest is located at the origin but at some height h. So stationarity does not change the distribution of the process if you change the origin, right? So we will assume that there is some UAV present at the origin but at a height h, and we will study the performance of this link where this blue triangle is the nearest base station of this red UAV. Okay, and there is one more thing called Slivniak's theorem. What it basically says is conditioned on this point, the rest of the process has same distribution as the original process. So if you look at the let me go back to that slide quickly. If you look at the workout example in the beginning, there was this example that was given, right? Conditioned on a point at origin, I'm asking you what is the probability that there is a point at -1, 1. So a simple form of Slivniak's theorem is that this probability is equal to probability that there is a point at -1, 1. So the distribution is same. So that's what the main gist is in the Slivniak's theorem. We will use that in the derivation. So it's like your independence property in the probability theory. So the system model I've already described it.
I just want to add one small context here.
Okay.
So this Slivniak's theorem is a direct consequence of the memorylessness property of the PPP.
Correct.
So if you remember the previous talk, we talked about three properties, right? One is the memorylessness, the second one is stationarity and isotropic, which is motion invariance, and the third one was ergodicity. So we are using memorylessness, we are using stationarity, and we are also using ergodicity. All of them are being used in this case, right? All these properties are being used implicitly to derive what is the average time that a base station needs to connect it to its serving UAV.
Okay.
Correct? So if the base station needs a lot of time, it means that the network design needs to be sort of redesigned rather to ensure that you have a much faster connectivity. So we're measuring latency, in other words. Okay. Yeah, I hope that aspect of it is cleared up. Okay. So yeah, how much time do we have, Professor Sai Prakash?
Actually, before that,
Yes.
this theorem tells something like bounds on the parameters?
Which theorem? Slivniak's theorem?
Yeah, Slivniak's theorem.
Yeah, Slivniak's theorem is concerning a very specific probability measure called the palm measure. So what it means is, so until now we have talked about like a point pattern.
It is a bounded problem. If it is a bounded problem,
it's not actually bounded. It is more to do with conditioning.
Conditioned.
Okay. So what we are saying is condition that the process has put a point in this area. What is the distribution of point patterns in some other part of space?
Okay.
Correct.
Okay.
So condition that there is a base
condition
station.
probabilities they might be used.
Yeah. So the conditional probabilities are actually kind of analyzed using what is called a palm reduced.
In most of the applications, we put it conditions only.
Condition only, right?
If
so
this
what
happens, that will happen.
Yes. So this Slivniak's theorem is like a version of this applying this kind of using this conditional distribution for the case when the PPP under consideration is a Poisson point process. Okay.
Means it is like he has derived something like Poisson process, some condition on Poisson process?
Yes.
Okay.
So what he's saying is condition that the Poisson process has a certain point at a certain location. What is the statistical properties of such a process? Because once you condition that the process has a point at a certain location, so to take the lattice example, okay, it will become very clear. If I told you that the lattice has, let's say you take a square lattice, right? That means all the integer points are fixed, right? If I told you that the lattice has a point at 1, then you are guaranteed that the lattice has a point at 2, at 3, at 4, and all. Right? But for a Poisson process, because it's memorylessness, even if you know that there is a point at a certain location, it does not change the statistics of the other points, right? Yeah. Just like in the one dimension also the same thing, right? Just because you know that a phone call has come now, doesn't tell you anything about how long it will take for the next phone call to come.
Yeah, that's true.
Right? So that property for a spatial case is generalized to Slivniak's theorem.
Yes.
Okay. So where it's being used here is she's actually fixing a particular base station and taking that base station and looking at the relay from that base station to its serving UAV and measuring the latency of that connection.
Okay.
And now she's taking every UAV connects to its nearest base station. And now we are asking what is the average latency across all the links, the left figure that you see here.
Okay.
Spatial average delay, right? That is what she is calculating. Okay.
Yeah, that I think his condition is good.
Yes.
Yeah,
yes.
right.
Yes.
So, shall we?
yeah.
You tell us that it's almost like 5 minutes more to 5.
Yes.
You just tell me at 5 we'll close it.
Actually, that's what I wanted to ask Taiba. So Taiba, I think you have a lot of material, right?
Yeah. 60 slides are there. She is halfway.
Yes. So how do you want to do it? Because I think both these papers are available online.
Right.
Yeah.
Okay. They're all this is published material. Okay. So I think this was in Globecom. The other is in ICASP. This year we are presenting it.
Yeah.
Okay.
Congrats.
So we can actually share the papers if they're interested, right? And the paper anyway we have discussed the slides, right? So my main request is to go and discuss the results, because now you're talking, you pose the problem, no? Now you talk about the results, and you kind of make sure that the next result for the ICASP result, you kind of build on it and say what is new. That way you can close it quickly.
Right.
So the other way I can put it, like the code she has shared. So I'll ask them to work and come back, and if there is question, I think they can directly contact Taiba Sheikh for.
But please put me in the loop so that
one afternoon or sometimes she
yeah.
gives half an hour. I can put a live session with them so that they can be answered.
Yeah. So maybe we can do one thing, right? So you can definitely do that. Yeah. Okay. Let's try to
share the presentation slides. I'll pass it on to the participants.
Yes.
And the codes also, what she shared, I'll just put it on to them. And let them run it and see if they have any questions. I'll come back to you, sir.
Yes.
Yeah,
that sounds like a good idea. Yeah. So Taiba, can you maybe spend maybe around 3-4 minutes for the results now, and maybe another 3-4 minutes by 5 let's close it. What do you say, Professor? What do you say, Professor Sai Prakash?
Yeah, that's fine, sir.
That's fine. Let's close it.
She has some work to do, so I just want to make sure that it should not be disturbed. But otherwise also, the majority of portion she has covered. And
yes, covered. The reason we wanted to give this example was
the result, if she keeps it, then we can spend few minutes and close it, sir.
Sorry?
If she presents some more results, if she wants, for 2-3 minutes, and then we can close it.
Okay, then why don't you go through the results quickly? Then?
Yeah, that's what.
That will make it faster, right?
Yeah.
Go for it.
So the first result is that So this is the mean delay I was mentioning in the first slide.
Go to the plots.
Okay.
We don't have time.
Okay.
Yeah.
Okay. Yes. So this is the mean delay I was mentioning in the first slide, the mean packet reception delay. The main takeaway here is that if you operate at a rate greater than some critical rate given by theta star, the mean delay will be infinite. So that is the first takeaway. The main background here is that if there are links, so many links with large distances, or if there are so many large links, then you are more likely to see a infinite mean delay. So that's a intuitive understanding of that. And this theta star, this threshold theta star, after which the mean delay is infinite, is purely a function of path loss exponent. It is not a function of base station density, or it is not a function of height of the UAV. It is purely a function of alpha. That is exactly why for any UAV height, once you cross this threshold, the mean delay is infinite. Similarly, for any lambda g.
Okay, next one.
So that's one thing. And and one more result is that with the increase in path loss exponent, we observed a decreased mean delay. The reason here is that as you increase your path loss exponent, as you operate in a higher denser regions, you see a reduced interference coming from the neighboring base stations because your alpha is very high. For that reason, the ratio S by I, the signal to interference ratio, would be very high that it would cross theta. That is the reason why, as you increase alpha, you see an unexpected decrease in the mean delay, and also associated with each alpha is a associated threshold theta, after which the mean delay is infinite. So this is one result in this paper. In the next work, what we have done was, instead of letting all the base stations talk to their UAVs, we had let we have assumed a random selection protocol where where each base station is either transmitting or not transmitting with a probability p. So if PG is chosen to be some 0.5, only 50% of the base stations are active and the rest are all inactive. One straightaway advantage that you see is that interference will be reduced, right? Only 50% of the base stations are transmitting, so you see a decrease in the interference. So you might expect an increase in the mean delay, but there is another contradicting factor that would increase the mean delay. I'll discuss that here. Yeah. So if we look at this slide, this PG corresponds to the probability with which the base station is active or not, and the x-axis is the theta transmission rate. You see if and also this PG equal to 1 corresponds to our previous work that I have just presented. We have generalized it here to some arbitrary PG. So as you reduce PG, although there are fewer number of base stations that are active, the amount of time each base station takes to become active is also large. As in, if P is 0.1 or if P is 0.5, so 1 by 0.5 is the amount of time on an average that a base station should wait to get its turn to transmit it to its own UAV itself. So that is a delay in addition to the packet reception delay that we saw previously. For that reason, although a decrease in P, with a decrease in P, you would expect a decrease in interference and thus an increase in mean delay. That is not the trend. That is what we wanted to show here. And also, as you decrease P, you get to transmit it at higher and higher transmission rate. So that is one advantage, but at the cost of increased mean delay. All this yellow shaded region corresponds to the higher mean delay. Previously, when you were at P equal to 1, you had a threshold up to some minus 2 dB. But with decreasing P, you are able to transmit until if suppose you are at 0.2, you are allowed to transmit until 10 dB, but with an increased mean delay, which is again a win. And again, with increase here, this plot is mean delay versus theta for varying h. With increase in h, we see a decrease in mean delay. Sorry, with increase in h, we see an increase in the mean delay. That's because your average signal power drops. But we see a contradictory result in the A to G. The reason for that is that in the system model, we have assumed the nearest association policy for the UAV U, right? For the air to ground link, it is always possible that there is another UAV here, V, which is closer to this base station than U. Imagine there is a UAV here by notation V, whose notation is V. That nearby UAV may cause more and more interference at the X, thereby increasing the mean delay. That is one reason why as you increase H, as you decrease H, the nearest interferer is closer to X, causing increased mean delay. Whereas in the G2A case, that is not the case. As you increase H, you will see a decrease in the mean delay. So you see these contradicting results. These contradicting results will ask you to design the network carefully, considering the base station density and the height of the UAV. And then the result here is for A to G, and PA is the probability with which a UAV is picked or not. The same result follows here. And one important point that I want to mention here is in G2A, this A of PG comma theta, or else the set of points for which the mean delay is finite, is independent of lambda G and lambda A. But here in A to G, it is a function of lambda G and lambda A. As in, if you have more and more, or else if you have more lambda G, since eta is lambda A by lambda G, you will get a lambda G in the numerator. As you have more lambda G, you will have more and more choices of P and theta for finite mean delay. But this would affect the G2A in an opposite way. Why? If lambda G is more, the interference on the from the ground is more on the G2A link. So this suggests you that you cannot arbitrarily choose any values of theta, PA, lambda G, and lambda A. There needs to be a careful selection of all these parameters, and this careful selection is given by this mathematical model, this way of deriving conditions on the finite mean delay. So that's the takeaway.
Okay, great. I think that is it. So basically what we are saying is you cannot have arbitrary because the geometry. Yes, exactly. So the big picture here is how do you design, when you want to design a UAV swarm talking to a set of terrestrial base stations, how should the channel access schemes be designed? How should the size of packets be designed for low latency communication?
Yeah.
Okay, so that is the one line sort of a problem statement, right?
Yeah.
All this analysis is basically to reduce those things into more mathematically tractable analysis.
Yes, sir.
Okay, so all of this can be cast like that. Okay, so yeah, so I think that's about it. So I hope we have not sort of gone too much over time.
Yeah,
I really thank Professor Sai Prakash Garu for giving us this opportunity.
I have to thank you, sir.
Yes,
I thank Ms. Tayaba Sheikh and Professor Sundar.
Yeah.
Because actually I know that Ms. Tayaba, there is a fasting going on, and I was actually planning in the morning, but the power cut has
No problem.
spoiled
Yeah,
it.
yeah.
And even afternoon also there is a small power cut and it has delayed.
No.
Thank you,
So
ma'am.
this is
Thank you for
no.
the
I think
nice invitation.
I think this is part of something we cannot control.
Yeah,
so
yeah.
that we should just let it go.
So,
Right.
I'll ask the participants, I'll pass on the course and ask them to go through
Yes,
it. And in
yes,
case of problem, I'll put it back, email to Ms. Tayaba
Yes,
for
yes,
that
yes.
clarifications.
Yes. So
Thank
Taiba, I think my one suggestion that I have is,
Yeah.
why don't you put all these codes in a Google Drive?
Yeah,
Yeah.
we are putting it, sir. No,
Yeah, you
she
put
has
it in
shared
Google Drive.
already, she has given the codes to me.
Okay,
She
I'm
has
asking you
sent a
to put
mail.
in Google Drive and give it to you so that it's accessible to anybody who wants to.
Right. We can just share the link. Yeah.
Actually, she
Yes.
has given the zip file to me.
Google Drive is better, no?
Yeah, okay, sir. Okay, sir, that is fine.
Then, yeah,
Because
no,
the
no,
Google
it's for you
Drive,
also.
the
It will be better.
participants will not get access. I will get access, sir.
Oh, I see.
Yeah. So,
Okay.
But
Yeah,
anyhow,
yeah.
sir,
Thanks
once
a lot.
again, thank you
Yeah,
very
yeah.
much, sir, for
This is good.
actually
Yeah.
accepting
You're
the
welcome.
invitation and giving a nice lecture. And I also thanks Ms. Tayaba for
Thank you, sir.
participating on the demos and some knowledgeable programming part.
Thank
you, sir.
sir.
Thank you very much, sir.
Yeah, thank you very much. If there's any questions, please feel free to reach
Yeah,
out.
sure, sir.
Okay?
I'll put it back
Yeah,
to you.
thank
Sir.
you.
Thank you, sir.
Yeah, thank you. Bye bye.
Any
Yeah.
questions? You want to ask any questions? No, thank you, sir. Sir, one more question, sir.
Yeah, please.
Yeah. So you want a process. What is the process followed for the data packet transfers from ground to air and air to ground? So
Process means?
as I understood, it's a random process, but anyhow, professor will speak about it.
What is the
So they want how the packets have been transferred from ground to air and air to ground. Is there any access mechanisms you are trying to use? Or?
Yes, good question.
Yeah.
So the way what we assume is if you open any data sheet corresponding to a modem, okay, you will have what are called waterfall curves. Are you familiar with this concept of waterfall curves? Basically, SNR versus packet error rate. Okay, so what any modem does is it will tell you if you give me this much SNR, I can give you this much of frame error rate. Correct. So what we do is we model that by having a situation where if the SNR exceeds a certain threshold, then the packet is received successfully. So it doesn't matter what specific modulation, whether you're using OFDM, it really does not matter. Okay. You can use OFDM, you can use OTFS, you can use MIMO, you can use some single carrier, doesn't matter really. So what we are doing is, we have simply assumed that you have a threshold behavior in terms of receiving the packet or not receiving the packet. The threshold is controlled by the theta, which is a SNR threshold. That theta is related to the size of the packet. Okay. So if the packet size is large, theta is large. If the packet size is small, theta is small. That is intuitive, correct? Right? So if I want to send a large packet, I need to have very good SNR because anywhere the packet has a problem, that entire packet is lost, right? So that is the model that we are using. Okay. Now, so that kind of, if you go back and look at our paper, we talk about basically a packet size which is given by log 1 plus theta. So you may ask, where is this log 1 plus theta coming? That is coming from Shannon's formula.
Yeah.
Okay. So that is, to put it in a nutshell, that is how we are assuming the transmission. And this is very commonly used, in most cases, even when you want to design something. Because you cannot assume every small thing about the modulation. So you assume something close to Shannon and you put a margin on that. Let us say you are 10 dB worse than Shannon, right? Then you'll still have log 1 plus SNR, but then SNR is 10 dB worse than what Shannon will give you. Okay. Any questions? I hope it's clear.
So I hope you understand that the theta value tells you whether the packet has to go for retransmission or it will be received properly. That's what sir was trying to explain. Is there any other question? No? Okay, sir. Thank you, sir. Thank you.
Yeah, thank you so much.
We'll close the session, sir.
Yes. Thank you.
Sir.
Bye-bye.
Thank you.
Yeah.
Thank you, sir.